The question says that a short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 to the power minus 2 joule. What is the magnitude of magnetic moment of the magnet? Now in this question there is a bar magnet that has been placed in the magnetic field and it is making a 30 degree angle due to the influence of the torque that this magnetic field is putting on this bar magnet. Now we have to find out what is the magnetic moment of this magnet. Torque equals to mb sine theta. Now in this question we have been given the torque on magnet, that is we have been given this value tau, theta we have been given, and we have been given the magnitude of magnetic field, that is b. So we only need to find out m, where m stands for magnetic dipole moment of this bar magnet. Now putting all those values in the given equation, we will get the value of m as 0.36 ampere meter square. Thank you. The question says that a short bar magnet of magnetic moment m equals to 0.32 joule per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar magnet is free to rotate in the plane of the field, which orientation would correspond to its stable or unstable equilibrium? What is the potential energy of the magnet in each case? Now a bar magnet is placed in the uniform magnetic field like in the previous exercise we saw, and the magnetic moment is given over here, and the magnitude of magnetic field is also given, that is 0.15 Tesla. Now we have to find out if the bar is free to rotate, now which orientation would correspond to its stable equilibrium and unstable equilibrium. And the second question is saying that what is the potential energy of magnet in each case. Now we know that a bar magnet in uniform magnetic field experiences a torque given by tau equals to mb sine theta, where m is the magnetic moment and b is the magnitude of magnetic field, and theta is the angle between magnetic moment and the magnetic field. And potential energy of the system is defined as minus mb cos theta, where m and b means same and theta means same as well. Now equilibrium, whether it is unstable or stable equilibrium, occurs when torque on the system is 0 or torque on the bar magnet is 0. Now we see that in this torque expression there is a component of sine theta. Now when sine theta is equals to 0, then this torque is going to be equal to 0. So sine theta is 0 in two cases, either theta is equals to 0 or theta equals to pi or 180 degree. Now when theta is equals to 0, the magnetic moment is parallel to the magnetic field, and when theta is 180 degree, then magnetic moment is anti-parallel to the magnetic field. Now theta 0 is called stable equilibrium and theta equals to 180 degree is called unstable equilibrium, because if we try to change the angle when it is at 180 degree, even a slight change would make it unstable, whereas if we try to change the angle when theta is equals to 0 degree, then it will restore to its same point at theta equals to 0. Finding out the potential energy of the system in stable as well as unstable equilibrium, since we have known the expression that the magnetic field of the system is given, the potential energy of the system is given by minus mb cos theta. So we can find out u for stable would be theta equals to 0, giving the expression of 0.048 joule minus of 0.048 joule, and for unstable it is 0.048 joule. Thank you. The question says that a closely wound solenoid of 800 tons and area of cross section 2.5 into 10 to the power minus 4 meter square carries a current of 3 ampere. Explain the sense in which solenoid acts like a bar magnet. What is its associated magnetic field? Now let's first understand what a solenoid is. A solenoid is a coil of wire designed to create a magnetic field when an electric current passes through it. The magnetic field inside the solenoid is uniform and resembles the field of a bar magnet. The resemblance occurs due to the alignment of magnetic field lines creating clear north and south pole. Now how does the solenoid mimic a bar magnet? When the current flows through the solenoid, it generates a magnetic dipole moment, and the solenoid behaves like a bar magnet with a distinct magnetic moment pointing from south to north pole along its axis, that is inside. Now magnetic moment is defined as m that is equals to N times I times A, where N is the number of turns of the wire of the coil and I is the current flowing through it, and A is the area of cross section of solenoid. That is area of cross section of solenoid is this. Now we have assumed here that this coil wounding is so tight that we can assume that each and every coil is a circle. So magnetic moment is defined as N times I times A. Now here the data has been given for the number of turns, the current in the solenoid, and the area of cross section. After substituting in this formula, we will get a value of 0.6 ampere meter square, which is the magnetic moment of this solenoid when the current is flowing through it. Thank you. The question is saying that if a solenoid in exercise 5.5, it is talking about the previous exercise, is free to turn about the vertical direction and the uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of torque on the solenoid when its axis makes an angle of 30 degree with the direction of applied field? Now previously we saw that there was a solenoid of 800 turns in which the current was flowing in the solenoid and it has a cross section area that was given. Now it was not subjected to any external magnetic field. Now in this question, that solenoid is subjected to external magnetic field of magnitude 0.25 Tesla. So we can assume the problem to be like this. Magnetic field is from left to right direction of 0.25 Tesla magnitude, and the solenoid is making 30 degrees. The axis of solenoid is making 30 degree with this magnetic field. Now we have to find out torque on the solenoid. Now we know that torque on a magnetic dipole in the magnetic field is given by tau equals to mb sine theta, where m is the magnetic dipole moment. Now here solenoid will act as a magnetic dipole with the given magnetic dipole moment, and b is the magnitude of magnetic field, that is 0.25 Tesla, and sine theta, where theta is the angle between the solenoid axis or the magnetic dipole and the magnetic field, external magnetic field. Now based on the previous data, we have the magnitude of magnetic dipole moment, that is 0.6, and we have been given the magnitude of magnetic field, external magnetic field, that is 0.25 Tesla and sine 30 degree. If we substitute these values in this formula, we will get the value of torque as 0.075 the Newton meter. Thank you. The question says that a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction and opposite to the field direction? And what is the torque on magnet in case 1 and 2? So here the question is saying that we have got a magnet which is under uniform magnetic field. So if we assume this to be the uniform magnetic field and this to be the magnetic axis, now we have to find amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction. So initially it was aligned in the magnetic field. Now we have to turn this magnet so as to align it perpendicular to the magnetic field. In the first case, normal to the field direction, and in the second case we have to align it opposite, that is from this state to this state. So upon turning the magnet normal and opposite, we have to find out what is the work done by external torque that is required. And the second question, we have to find out what is the torque on the magnet in case of 1 and 2. Now in second case we have to determine if we have turned this magnet, then what would be the torque acting on this magnet. In the first case like this in 90 degree, and in the second case that is theta equals to 180 degree, where theta is the angle between the axis of the magnet and the uniform magnetic field. Now we know that torque on a magnet is given by tau equals to mb sine theta, where m is the magnetic moment, b is the magnitude of the magnetic field, and sine theta, where theta is the angle between the magnetic moment of the magnet and the magnetic field. We also know that work done by external torque is equals to final potential energy minus initial potential energy. and the magnetic potential energy is defined as U equals to minus mv cos theta, where m is the magnetic moment, b is the magnitude of magnetic field, and theta is again the angle between m and b. So let's proceed to solving. So work required by the external torque in aligning the magnet normal to the field, that is from theta equals to 0 degree to theta equals to 90 degree. We will find the initial and final potential energies. Initial potential energy will correspond to the theta equals to 0 degree, and final potential energy will correspond when theta equals to 90 degree. So using the formula above, we have calculated U initial, that is equals to minus 0.33 joule, and U final would be equal to 0 joule, because cos 90 would be equal to 0. Now work done would be equal to U final minus U initial, and that would give us 0.33 joule. Now similarly, we will proceed to the second question that said that from theta equals to 0 degree to theta equals to 180 degree. So using the same approach, we will find the U initial, that is when theta equals to 0 degree, it would be equal to minus 0.33 joule, and U final would be equal to 0.33 joule. So the work done would be 0.33 joule minus of 0.33 joule, that would give us 0.66 joule. Now the second part question said that what is the torque on the magnet when theta is equals to 90 degree and when theta equals to 180 degree. So we saw earlier that torque is defined as mb sin theta, or the cross product of magnetic moment and the magnetic field. Here m is the magnitude of magnetic moment and b is the magnitude of magnetic field, and sin theta, where theta is the angle between m and b. So when theta equals to 90 degree, we will get torque of 0.33 Newton meter, and when theta equals to 180 degree, we will get a torque of 0 Newton meter. Or visualizing this, when the magnet is in this state, we will get a torque of 0.33 Newton meter, and when the magnet is in this state, that is opposite to the magnetic field, we will get a torque of 0 Newton meter. We also know that this position is the unstable equilibrium position. Thank you. The question says that a closely wound solenoid of 2000 turns, an area of cross section 1.6 into 10 to the power minus 4 meter square, carrying a current of 4 ampere, is suspended through its center, allowing it to turn in a horizontal plane. Now we have to find out what is the magnetic moment associated with the solenoid, and what is the force and torque on the solenoid if the uniform horizontal magnetic field of 7.5 into 10 to the power minus 2 Tesla is set up at an angle of 30 degree with the axis of solenoid. So there is a solenoid, and that is hanging. So we can assume from the top view that the solenoid is this is the solenoid, and a uniform magnetic field of magnitude this much, that is 7.5 into 10 to the power minus 2 Tesla, is set up at an angle of 30 degree. The angle between this solenoid axis and the magnetic field is 30 degree, and we have to find out what is the magnetic moment associated with the solenoid. So magnetic moment will not be influenced by the magnetic field. So magnetic moment is defined as m equals to NIA, where n is the number of turn of the solenoid and I is the current flowing through it, and A is the area of cross section of the solenoid. We have been given the data, all three data, so we can find out the magnetic moment. And the second question says that what is the force and torque on the solenoid when this magnetic field is set up. So torque on the magnetic dipole is given by mb sin theta, that is m is the magnitude of magnetic moment and b is the magnitude of magnetic field, and theta is the angle between the magnetic moment and the magnetic field, and here it is theta equals to 30 degree. We also need to tell what is the force on the solenoid. So we know that since the magnetic field is uniform, no net force would be acting on this solenoid by the uniform magnetic field. So force is going to be 0. Now let us calculate the magnetic moment and torque on the solenoid. So magnetic moment would be equal to NIA, where n equals to 2000 and I is 4 ampere and area of cross section is 1.6 into 10 to the power minus 4 meter square. So we will get a value of 1.28 ampere meter square. And the second question said that what is the torque on the solenoid. Since we know that the magnetic field is uniform, so force is going to be 0. So calculating torque, we can use the formula mb sin theta, where m is 1.28 and the magnetic field is 7.5 into 10 to the power minus 2, that is given. So we will get a value of 4.8 into 10 to the power minus 2 Newton meter torque. Thank you. The question says that a short bar magnet has a magnetic moment of 0.48 joule per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance of 10 cm from the center of the magnet on the axis and as well as the equatorial lines of the magnet. So if we assume that this is our magnet, bar magnet, and we have to find out the magnetic field at a point which is on the axis and on the equatorial line, that is the perpendicular bisector of the magnet. Now, for a fact, we know that a short bar magnet behaves as a magnetic dipole with a magnetic moment m. Now, magnetic field at a point on axis or the bisector or the perpendicular bisector is given by the formula. B on axis is mu naught by 4 pi multiplied by 2 into magnetic moment of the magnet divided by r cube, and on the equatorial position it is given by mu naught m by 4 pi r cube, where r is the distance from the center of the magnet to that point and m is the magnetic moment of the bar magnet. Now, using this formula we can easily find out what is the magnetic field or the magnitude of magnetic field on the axis and on the equatorial point. So substituting the formula, we will get the magnetic moment on the axis as 9.6 into 10 to the power minus 5 Tesla, which will be along the magnetic moment, and on the equatorial position it will be 4.8 into 10 to the power minus 5 Tesla, which will be directed opposite to that of the magnetic moment of the magnet. Thank you. The question says that a short bar magnet placed in the horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 cm away from the center of the magnet. The Earth's magnetic field at the place is 0.36 Gauss and the angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point? That is from 14 cm from the center of the magnet. The question is hinting that it has given the magnetic field at the axis and we have to find out the magnetic field at the perpendicular bisector of the bar magnet. At 14 cm away from the center of the axis, there is a null point. And what is null point? Null point is the field due to a magnet is equal and opposite to the horizontal component of the Earth's magnetic field. Since the dip angle is 0, at null point, the net magnetic field is going to be 0. That is, the magnitude of magnetic field due to the bar magnet would be equal to the magnitude of magnetic field of the Earth's magnetic field, and its direction will be opposite. That's why it will cancel out each other. So in that way we have been hinted the magnitude of magnetic field at the axis of the bar magnet at 14 cm. And also we know that B at axis, magnitude of magnetic field at the axial position is given by mu naught 2m by 4 pi r cube, where m is the magnitude of magnetic moment, and at the equatorial position it is given by mu naught m by 4 pi r cube, and B at axis is equals to 2 into B at equatorial position. That is, B at axis is 2 times that of the B at equatorial point, where r is same. That is, if we find out the magnitude of magnetic field at the 10 cm away from the center of the magnet on the axial position, then let's assume that its magnitude is A. Then the magnitude of magnetic field at the equatorial position at the 10 cm away from the center would be equal to A by 2. So let's proceed. If at 14 cm from the center of the magnet there is a null point, then B at axis at 14 cm must be equal to B at Earth, as we said, and that will be equal to 0.36 into 10 to the power minus 4 Tesla in opposite direction from that of the Earth's magnetic field. So we will get this expression, that is mu naught 2m by 4 pi r cube would be equal to 0.36 into 10 to the power minus 4 Tesla. Now total magnetic field at the normal bisector or the equatorial position at 14 cm is given by the magnetic field due to the Earth plus the magnetic field due to the bar magnet. At the equatorial position, the direction of magnetic field by the bar magnet will be equal to the direction of magnetic field by the Earth, so they both will add up. Now the total magnetic field would be contributed by that of the Earth and the magnetic field by the magnet. Since we know that B by earth would be equal to 0.36 Gauss, and B at magnet would be equal to half of that of the B at axis, and B at axis is 0.36 Gauss, so it would be equal to 0.18 Gauss. So the total magnetic field would be 0.54 Gauss. Thank you. The question says that if the bar magnet in exercise 5.13 is turned by 180 degree, where will the dew points be located? So basically it is referring to the previous exercise, that is 5.8. So in that question there was this bar magnet which was in the horizontal position with the magnetic field, and the null point was on the axis. And if we assume that this was the direction of magnetic field due to the bar magnet, that is Bm, we have shown it by that Bm. So the Earth's magnetic field was in the opposite direction, so on the axis there was the null point. So now the magnet has been reversed to 180 degree. So now its magnetic field on the axis has a direction opposite to that of the initial direction. That is, now it is from right to left, which can be seen over here. Now we have to find out new null point. So we know that at null point the net magnetic field is 0, that is magnetic field due to the magnet will cancel out the magnetic field due to the earth. So we have to find out at what point the magnetic field will be 0, the total magnetic field will be 0, or the null point of the magnet. So it will be on the equatorial position now, because along the axis the magnetic field gets aligned, the direction of magnetic field is same to that of the Earth's magnetic field, so we can't find it on the axial position, so it will be on the equatorial position. Now B at equatorial position is given by mu naught m by 4 pi r cube, where r is the distance from the center of the magnet. Now here we have to find out at what point r1 will the magnetic field due to the magnet will be equal to 0.36 into 10 to the power minus 4 Tesla, or the Earth's magnetic field, or the magnitude of Earth's magnetic field. So we have to find out r1 over here. Now we know from the previous question that mu naught into 2m by 4 pi r cube was equal to 0.36 into 10 to the power minus 4 Tesla, where r was 14 centimeter. So this is the magnetic field on the axis of the magnet, which was the case in the previous question. At r equals to 14 there was a null point, so it equals the magnitude of magnetic field to the earth. So we know this. Now we have to find out r1 for the same magnitude of magnetic field. So when we divide this both equations, we will get 0.14 meter or 14 centimeter by r1 cube, that is, this is the unknown, would be equal to 2. So from this equation we can find out r1, which will be equal to 11.1 centimeter. That is, the new null point will be at the equatorial position at 11.1 centimeter away from the center of the magnet. Thank you. The question says that predict the direction of induced current in the situation described by the following figure 6.15 from A to F. Now there are 6 figures. In all these figures we have to find out what is the direction of induced current in the coil upon either a moving magnet or there is change in current in the nearby circuit. So we will use Lenz's law to find out the direction of current, and Lenz's law says that the direction of induced EMF will oppose the change in flux that created it. For example, we can see the demonstration over here. Like if the north pole of the bar magnet is coming close to a coil which is stationary, now we see that the flux is increasing, so the current will be induced in this coil such that north pole will be created over here, so that it will oppose the moving magnet towards it. So the current will flow in the direction that would create stronger north pole over here. Now similarly, when the magnet will move away from this coil, then south pole will be there because it will oppose the motion, then it will create a south pole over here so that it attracts the moving magnet and it opposes the movement of the magnet. So let's use this to find out what is the direction of current in each of these diagrams. So in the first diagram we see that the south pole of the magnet is approaching over the Q side of the circuit, So we can see from this figure that since south pole is coming near, so this current, induced current, will be such that south pole will be created over here momentarily, so that the direction, the movement of bar magnet will be opposed. So in order to create south pole over here, north pole must be created over here. So if we apply the right hand thumb rule, we can see that in order to create north pole in the left side, the current must flow through in this direction, anti-clockwise direction, that is QRP. So the current, the direction of current is going to be QRP and Q again. Similarly, in this figure, we see that south pole is moving towards the Q point. So again, the induced current will be produced such that south pole gets created over here, and north pole gets created over here. So we can say that from the right hand thumb rule, the current will flow from PRQ in this circuit, and since north pole is moving away from this coil as in this diagram, so south pole will be created over here. So in order to create the south pole over here, north pole must be created over here, and applying the right hand thumb rule, we can say that the current will be in anti-clockwise direction in this circuit, which means that the current will flow from Y, Z and X. Let's move to the next figure. In this figure, we have tapping key just closed. Now here tapping, if the tapping key just got closed, it means the current started flowing, and when current start flowing, we see that the flowing current will create north pole over here and south pole over here. So the induced current in this circuit will be such that north pole gets created over here and south pole gets created over here. And by applying right hand thumb rule, we can say that again, in order to create north pole over here, the current should be in this direction, so it should be Y, Z, X. Now in this question, we see that rheostat settings being changed. So the pointer is decreasing the resistance, it means the current would be increasing in here, and this axis, in this axis, YZ segment of this coil is much away from us than YX section of this coil. So if the current is increasing over here, north pole will be created over here and south pole will be created over here, and again we can say that north pole should be created in this coil over here and south pole should be created over here. Now since it is much nearer to us, so in order to create the north pole, the current must flow through YXZ, or we can say that the current will flow from, the direction of current will be from YXZ and again Y. Now in this diagram, we see that tapping key just released, or we can say that the current has just stopped. Now earlier when the current was flowing, we can see that this wire is hidden from the solenoid. It means that the circular turn is like this. Now earlier when the current was flowing, it would be such that the north pole should be here by right hand thumb rule, and south pole would be here. Now just after releasing this tap key, north pole has decreased, or we can say that the north pole of the magnet has been released. So south pole will be created over here and north pole will be created over here, and for creating south pole over here, we can say that the direction of the current must be in this opposite direction, or X, R, Y direction. And in this sixth figure F, we see that current is decreasing at the steady state. Now here in this line, the magnetic field direction would be such that the magnetic field will be 90 degree to the area vector of this coil. So we can see in this diagram that if that is the case, phi is going to be 0, as phi is the dot product of magnetic field and the area vector. So there would be no current that is produced in this circuit, in this coil. Thank you. The question says that use Lenz's law to determine the direction of induced current in situations described in figure 6.16. A wire of irregular shape turning into a circular shape. This figure describes a wire that is of irregular shape and it is turning back into a circular shape. And the second question is a circular loop being deformed into a narrow straight wire. So earlier it was a circular loop, now it has been transformed into a straight wire. So we have to find out what would be the direction of induced current in both the cases. In the first case, the magnetic field lines are going into the plane, and in the second case it is coming out of the plane. Now we will be using Faraday's law and Lenz's law in order to understand and find out what would be the direction of current in this cases. The Faraday's law says that the EMF, induced EMF, due to which the current would flow, would be equal to minus of d phi by dt, where d phi is the change in flux and where flux is the dot product of magnetic field and the area vector. And Lenz's law says that the direction of induced current will oppose the change in flux that created it. So we will have to focus on the flux and how it is changing, and the flux will be opposed, the change in flux will be opposed. That's how the current will be produced. So in the first case, we see that irregular shaped wire, when it turns out to be a circular shape, then the area will increase, or as flux was defined as B dot A. So since area will increase, d phi or phi will increase. So the induced current will oppose the increase in phi or the flux, or opposite magnetic field will be created. So initially the magnetic field was going into the plane, so magnetic field out of the plane will be created, and thus in order to create magnetic field out of the plane, that is coming out of the plane, the current has to flow in anti-clockwise direction, that is A, D, C and B. So by applying right hand thumb rule, we can say that if the current flows in anti-clockwise direction, then the magnetic field will be coming outward, and that's how the current will be induced. The current will be induced. In the second case, it says that the area is decreased or flux is decreasing, d phi is decreasing. So the induced current will support the flux to restrict it from decreasing, and thus the magnetic field will be in the same direction as before, or the magnetic field will continue to be out of the plane, and thus we will say that in order to have magnetic field out of the plane, just like before, the anti-clockwise direction current should flow, or A dash, D dash, C dash, B dash should be the direction of current. Thank you. The question says that a long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds, what is the induced EMF in the loop while the current is changing? So here there is a small loop of wire of area 2 centimeter square is placed inside a solenoid. So just imagine that if solenoid is seen from its left or right along the axis as this, then there is a small loop of wire of 2 centimeter square placed inside the solenoid. Now we have to find out what is the induced EMF in this small wire, subjected that the current in this solenoid is changing from 2 ampere to 4 ampere in 0.1 second. Now if the current is changing, then obviously the magnetic field is going to be changing. Now if magnetic field is going to be changing, then there is a flux that is changing inside this loop as well, and flux is changing with time, so there will be induced EMF. Now Faraday's laws of electromagnetic induction says that the induced EMF E in the closed loop is proportional to the rate of change of magnetic flux phi b through the loop, and that is given by induced EMF is equals to minus d phi by dt. Now magnetic field inside the solenoid is given by B equals to mu naught Ni, where mu naught is the permeability of the free space, N is the number of turns per unit length of the solenoid, and I is the current. Now magnetic flux is defined as phi b equals to b dot a, that is the dot product of magnetic field and the area vector. Now for loop normal to the solenoid, as in the case of our question, theta is equals to 0, so the dot product will result out to be BA, as cos theta is equals to 1. Now let's calculate the induced EMF. So as we knew that induced EMF is given by minus d phi by dt, so we have to calculate the change in flux and we have to divide it by time, duration of time. So change in flux, we can see that, and since current is changing from 2 ampere to 4 ampere, so this value determines the delta t, and this is the number of turns per unit length in the solenoid, and this is the mu naught. So this results out to be the magnetic field of the solenoid, 4 pi 10 to the power minus 7 multiplied by 1500 into 2.0. So here 1500 comes from this data that has been given in the question, 15 turns per centimeter. Now if we divide, it has been given that 15 turns per centimeter. Now if we turn this centimeter to meter, then we will get 15 meter equals to 100 centimeters. So we will have to multiply it with 100, so we will get 1500 turns. So that's how we got 1500 multiplied by the area of the coil, that is 2 into 10 to the power minus 4 Weber, divided by time, duration of time, that is 0.1 seconds. So here we will get 7.54 microvolt. Thank you. The question says that a rectangular wire loop of side 8 cm and 2 cm with a small cut is moving out of the region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 cm per second in the direction normal to the longer side and shorter side of the loop? For how long does the induced voltage last in each case? So here magnetic field is normal to a rectangular loop. I have shown it with a magnetic field going into the plane, and the rectangular loop is lying on the plane of the paper of side 8 cm and 2 cm. The loop is placed normally to the magnetic field. Now when this loop is taken out of the magnetic field in either way, like in this way, parallel to the 2 cm side and parallel to the 8 cm side, so we have to calculate what is the induced EMF in both the cases, and also we have to find out what would be for how long does the induced voltage last. So we know that the EMF induced in a moving conductor in a magnetic field is given by this formula, E equals to minus d phi by dt. If the loop moves out of the magnetic field, then it is given that this expression turns out to be B times L times V, where B is the magnitude of magnetic field and L is the side of the parallel to motion and V is the velocity of the loop. Now there are two cases. At first, the movement is parallel to the 2 cm, or longer side is normal to the motion, that is movement is along 2 cm. So in this case, the velocity, we have been given the velocity, we have been given the B, and we have also been given the L, that is length of the side parallel to the motion. In this case, L is going to be 0.08 meter and magnitude of magnetic field is 0.3 Tesla and velocity is always 0.01 meter per second. So we will get the answer to be 2.4 into 10 to the power minus 4 volt in this case. Now the question also asked duration of the induced voltage. Now for the time the flux will change, there will be induced voltage. Now for how long will the flux change? Starting from the movement of the coil till the coil has moved 100% out of the magnetic field, there will be the induced voltage. Now since this side is moving out of the magnetic field, so we can get the time with by dividing the velocity from 2 cm. So 2 cm by 1 cm per second, we will get 2 seconds. Similarly, for shorter side normal to motion is given by BLV, where L is the length of side parallel to the motion. Now in this case, it is going to be 0.02 meter. Rest of the things will remain same. And similarly, in this case also, since the motion will be in this direction, now this side will go out of the magnetic field. Now how long will it take? 8 centimeter by the speed, that is 0.01 meter per second. So we will get time duration of 8 seconds. So 6.6 into 10 to the power minus 5 volt will remain for 8 seconds. Thank you. The question is saying that a 1 meter long metallic rod is rotated about an angular frequency of 400 radians per second about an axis normal to the rod passing through its one end. The other end of the rod is in contact with the circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. We have to calculate the EMF developed between the center and the ring. Now there is a rod which is rotating about one of its end, and there is another end which is in contact with the axis, which is in contact with the ring, which has not been drawn in the picture. So we have to calculate the EMF generated between this point and this point 1 and 2. Now under given conditions, and the condition is there is a magnetic field that is parallel to the axis of rotation of the rod of magnitude 0.5 Tesla. So the magnitude of this magnetic field is 0.5 Tesla, and the omega is 400 radians per second. That has been given in the question. So we know by Faraday's laws of magnetic induction that EMF is induced when the conductor moves in the magnetic field, and induced EMF depends on the relative motion of the conductor and the magnetic field. And the formula for electromagnetic induction as per the Faraday's law is given by E, or the EMF, is equals to minus of d phi by dt, where phi is the flux, magnetic flux, defined as B dot A, where B is the magnetic field and A is the area vector. And now in this present case, the rod sweeps out an area as it rotates, changing the magnetic flux through it. Now, for the sake of this question, we will consider a rod of length L. We haven't given the measurement of this length, that is 1 meter. So let us assume that this is the length of the rod L, and there is a small element of length dx at a distance that is x from the axis of rotation. Now the motional EMF that is generated in this section is given by E is equals to B VL. We know that this is the formula for motional EMF. Now for this section, for the section of length dx, it would be equal to V times dx times B. Now V at the distance x in a circular rotation is given by V is equals to omega times x. So we can write it as B times omega x times L that is x. Now we will have to integrate this expression from 0 to L for the entire length of the rod. So total EMF would be equal to integration of B omega x dx from 0 to L, where B is the magnetic field, omega x is the V part of this formula, and dx is the length of the small section of the rod. Now after this integration, we will find out that EMF is equals to B omega L square by 2. And after substituting the values, we will get the value of 100 volts. So this is the EMF developed between the center and the ring. The question says that a horizontal straight wire 10 centimeter long extending from east to west is falling with a speed of 5 meter per second at right angles to the horizontal component of the Earth's magnetic field, that is 0.30 Weber per meter square. What is the instantaneous value of EMF induced in the wire? What is the direction of EMF, and which end of the wire is at the higher electrical potential? So in this question, it has been given that a wire of 10 meter in length, this wire, let us assume that this is 10 meter in length, it is falling down with a speed of 5 meter per second, and it is subjected to a uniform magnetic field of magnitude 0.30 into 10 to the power minus 4 Weber per meter square. Now we have to find out what is the induced value of EMF in this wire. So we know that when a conductor moves in a magnetic field, and EMF is induced due to the relative motion between the conductor and the magnetic field. Now Faraday's laws of electromagnetic induction says that the induced EMF is equals to minus of d phi by dt. In this case, the motional EMF would be equal to BVL, where the direction of magnetic field and velocity of the wire is perpendicular to each other, and this is the length of the wire. So let's calculate the instantaneous value of induced EMF. So using the formula above, we know that E is equals to BVL. sine theta. Sine theta here comes from the cross product of V and B, that is V cross B. So here we know that theta is 90 degree because the wire is falling down, and we have to calculate the EMF due to the magnetic field and due to the horizontal component of the magnetic field, Earth's magnetic field. So the theta will be equal to 90 degree here. Now L is going to be 10 meter because this is the length of the wire that has been given, and V is the velocity at which it is falling, and B is the magnitude of magnetic field. Now substituting in this formula, we will get a value of 1.5 into 10 to the power minus 3 volts. Now for the direction of EMF, using the right hand thumb rule as well. So this is a vector of V, this is vector B, and this is 90 degree between them. Now if the right hand thumb rule says that the cross product of the two vectors is, the direction of cross product of two vector is along the thumb. So when V cross B is there, then the direction will come from west to east. That's how we know that the EMF is directed from west to east. Now the third question was higher potential end of the wire. The direction of the induced EMF determines the higher potential end. Since the EMF is directed from west to east, the eastern point of the wire is going to be at the higher potential. So this point, eastern point, is going to be at the higher potential. Thank you. The question says that current in a circuit falls from 5 ampere to 0 ampere in 0.1 seconds. If the average EMF of 200 volt is induced, give an estimate of the self-inductance of the circuit. Now we know that self-inductance is a property of the circuit where the change in circuit induces an EMF in the same circuit. Now Faraday's laws of electromagnetic induction says that induced EMF would be equal to E equal to minus of L delta I by delta T, where delta I is the change in current and delta T is the duration in which this change in current has occurred, and E is the induced EMF and L is the inductance of the circuit. Now we have to find out, give the estimate of self-inductance, that is we have to find out the value of L in Henry, which is the self-inductance. So we have been given the data of initial current, that is 5 ampere, final current, that is 0 ampere, since the current dropped from 5 ampere to 0 ampere in 0.1 second. So delta T, duration of time, would be equal to 0.1 second. Now average EMF is given, that is 200 volts. So after substituting these values in this formula, we will get a value of L, that is equals to 4 Henry. Thank you. The question says that a pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current in one coil changes from 0 to 20 ampere in 0.5 seconds, what is the change of flux linkage with the other coil? Now mutual inductance, we know that it is a property of pair of coils that quantifies the ability of one coil to induce an EMF in the another coil due to the changing in current. So as there is a change in current in this coil, then the associated magnetic flux will change, and that changing magnetic flux will induce EMF, because we know that by Faraday's law, EMF is given by minus of d phi by dt. Since this change in flux will interact with the second coil, and this change will happen with time, so an associated EMF will induce in another coil. Now in this question, we have to find out what is the change of flux linkage. So we have to find out the change in flux. Now flux is given by mutual inductance times the current. Now change in flux can be given by mutual inductance multiplied with the change in current. Now here we have been given the mutual inductance, that is 1.5 Henry, and we have also been given the change in current, that is 0 to 20 ampere. So final current is 20 ampere and the initial current is 0 ampere. So we can easily find out using this formula the change in flux linkage, that would be equal to 1.5 times 20, and that will be equal to 30 Weber. Thank you. The question says that a 100 ohm resistor is connected to a 200 volt 50 Hz AC supply. What is the RMS value of the current in the circuit, and what is the net power consumed over full cycle? Now if we try to represent it in a circuit diagram, then it is like this. This is the AC supply of 50 Hz and 220 volt. Now unless it's specified, this voltage is in the RMS form, and there is a resistor of 100 ohm which is connected to the circuit in a series circuit. To express the AC power in the same form as DC power, RMS value is used, and RMS is defined as the square root of the average of a squared quantity. IT, if we define current varying with time as Im sin omega t, where Im is the peak current and sin omega t is the sinusoidally varying quantity. Now I RMS square would be equal to 1 by t of integration from 0 to time period, where t is the time period, Im squared sin squared omega t dt. Now if we find out this integration, definite integration, then we will come to know that IRMS squared would be equal to Im squared by 2, or we can say that IRMS is equals to peak current by root 2. Now in this question we have been given the VRMS, that is 220 volt, and the resistance, that is 100 ohm, and the frequency. So we have to find out IRMS. Now IRMS can be given as VRMS by R. So VRMS is 220 volt and 100 ohm is the resistance, so it is equals to 2.2 ampere. Now net power can be given by the formula IRMS squared times R, where we know that IRMS is equals to 2.2 ampere. So upon substitution we will get a value of 484 watts. Thank you. The question is saying that the peak voltage of an AC supply is 300 volt. What is the RMS voltage? And the RMS value of the current in the circuit is 10 ampere. What is the peak current? So we saw this derivation in the earlier question of the RMS value of current. Now RMS value in AC current is used to make it equivalent to the DC current, so that the formula for current and power can be used. So we have to find out here peak voltage of an AC supply at 300 volt. So from this derivation we came to know in the previous question that IRMS is equals to Im, or the peak current, divided by root 2. So here we have to find out what is the, now this goes same with the voltage, that is VRMS would be equal to V peak divided by under root 2. Now the question asked what is the RMS value of voltage, that is VRMS. We have to find out VRMS, and we have been given the peak voltage of 300 volt. So upon using this formula we will get to know that the VRMS is equals to 212.1 volt, and the second question was the RMS value of the current is given and we have to find out peak current. So again using this formula, in this question we have been given the RMS value, so we will have to find out Im. So rearranging this we will get to know that Im, or the peak current, is equals to 14.14 ampere. Thank you. The question says that a 44 millihenry inductor is connected to 220 volt 50 hertz AC supply. Determine the RMS value of the current in the circuit. Now we can pictorially represent this question in this form, like this is the AC supply of 200 volt and 50 hertz, and the inductor is connected in a series circuit, and the value of inductance is 44 millihenry. Now we have to calculate what is the RMS value of the current in the circuit. Now if we make it equivalent to the DC circuit, then we can see that there we have found out the questions, we have found out the solution of the questions in which this was the resistance and this was the cell. So inductor also possesses some resistance, that is known as inductive reactance XL, and that is defined as omega times L, where L is the inductance and omega is the 2 pi by T, or 2 pi times frequency. Now this inductor will pose this much quantity of resistance, and the inductive reactance is also having the same unit of ohm. Now RMS current would be equal to VRMS by XL, as XL is representing the resistance in the circuit. So we can find out the RMS current using this formula, that is VRMS by XL. We haven't given the VRMS, that is 220 volt, and XL we have to find out, that is inductive reactance. Now inductive reactance can be found out as we have been given the value of L, that is 44 millihenry, and we haven't given the value of omega as well, because omega, as I said, that it is 2 pi times frequency. So 2 pi is 2 into 3.14 times frequency is given, that is 50 hertz. So the value of XL is going to be 2 pi 50 multiplied by 44 into 10 to the power minus 3, because it is 44 millihenry. Now upon calculating, we will get the value of XL as 13.82 ohm. Now IRMS is equals to VRMS divided by XL. So VRMS is equals to 220 volt, which is given in the question, and XL is 13.82 ohm. So the answer would be 15.92 ampere. Thank you. The question says that a 60 microfarad capacitor is connected to a 110 volt 60 hertz AC supply. Determine the RMS value of the current in the circuit. Now again, this question is similar to the previous question. Again, this capacitor is going to resist some kind of current, and that resistance is given by capacitive reactance, that is XC, and it is defined as 1 by omega C, where omega is 2 pi times frequency. Now again, since this represents the resistance in the circuit, we can give the expression for current as voltage divided by resistance, that is IRMS is equals to VRMS by XC. Now here we have to find out the capacitive reactance, that is XC, and since VRMS is given, we will substitute in the given formula and find out the value of IRMS. Now calculating XC, we will get the value of 44.2 ohm. Now calculating IRMS, that is current, using the formula VRMS by XC, we will get a value of 2.49 ampere. Thank you. The question says that in exercises 7.3 and 7.4, what is the net power absorbed by each circuit over a complete cycle? Explain your answer. Now in both these exercises, we saw that in exercise 7.3 there was an inductor in the series with the source EMF, and in exercise number 7.4 we saw that there was a capacitor in series with the source EMF. Now we have to find out what is the net power absorbed by each circuit over a complete cycle. We have to explain this answer. Now we know that power in AC circuit is given by the formula, that is IRMS multiplied by VRMS multiplied by cos phi, where phi is the phase difference between the source and the circuit. Now for a purely reactive circuit, let us assume that the first case of 7.3, that is a inductive circuit, we saw that current lags by the voltage of pi by 2, or the phase difference between the source current and the circuit is pi by 2. Now similarly, we saw that in the capacitive circuits, the current leads the voltage by pi by 2. That is, here the current is leading by pi by 2. Now in both the cases, we saw that there is a phase difference of pi by 2. Now average power, as discussed earlier, is given by VRMS times IRMS times the cos of phase difference. Now cos of pi by 2 is also always going to be equal to 0, since cos pi by 2 is 0. So we can say that power average is equals to 0 in purely reactive circuits. Thank you. The question says that a charged 30 microfarad capacitor is connected to a 27 microhenry inductor. What is the angular frequency of free oscillation of the circuit? Now free oscillations happen when the energy exchange between capacitor and a charged capacitor and an inductor is happening in the circuit. Now this only happens in purely reactive circuit. Now a capacitor and an inductor forms an oscillatory circuit with energy exchange between the electric and magnetic fields. Now angular frequency of the oscillation is determined by this governing equation. So this is basically the implication of Kirchhoff's law. So we know that EMF around the inductor is given by L di by dt. Now dq by dt is equals to L, so it is L di by dt. That is the double differentiation of charge will give us the, with respect to time, will give us the differentiation of current with time, that is L di by dt, plus q by v. This is the potential difference across the capacitor. Now we will come to the conclusion that omega from this governing equation is 1 by LC. That is the angular frequency of natural oscillation in this reactive circuit is going to be 1 by under root LC. Now upon substituting this in the given formula, we will come to know that omega is equals to 1.1 into 10 to the power 4 radians per second. Thank you. The question is saying that a series LCR circuit with resistance of 20 ohm, inductance of 1.5 Henry and capacitance of 35 microfarad is connected to a variable frequency of 200 volt AC supply. When the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred to the circuit in one complete cycle? Now this question can be pictorially represented like this, where this is the power supply, AC power supply of 200 volts, and the frequency is variable over here. Now we have to find out the frequency at which the natural frequency of the circuit meets or the resonance happen. And at resonance, what is the average power transferred to the circuit in one complete cycle? Now we know that resonance in the LRC circuit, that resonance occurs when the inductive reactance equals the capacitive reactance, or mathematically we can represent it as inductive reactance is equals to capacitive reactance. When the inductive reactance and the capacitive reactance matches, the impedance is equals to resistance, or it is purely resistive. So upon equating these two quantities, we will get omega, or the frequency, is equals to 1 by under root LC. Now we can find out the frequency at which the resonance happens by this formula, applying this formula, and after that the power given to the circuit, we have to find out what is the average power transferred to the circuit in one complete cycle. Now when this happens, since the impedance is equals to the resistance of the circuit, so power would be equal to V square by Z, or Z can be equivalent to resistance because there is no other resistance that is happening in the circuit. So R will be equal to, or Z will be equal to 20 ohm. Now upon using this formula for omega, we will find out the value of the resonance frequency about 1380.2 radians per second, and power, we can use this formula of V square by Z, and that will give us, since this is the given quantity 200 volt and Z is equals to the resistance, that is 20 ohm, we will get a value of 2000 watts. So at resonance in this LCR circuit, the average power transfer to the circuit is in one complete cycle is going to be 2000 watts. Thank you. The question says figure 7.17 shows a series LCR circuit connected to a variable frequency 230 volt source where inductance is 5 Henry, capacitance is 80 microfarad and resistance is 40 ohm. We have to determine the source frequency which drives the circuit in resonance, obtain the impedance of the circuit and the amplitude of the current at the resonant frequency, and determine the RMS potential drop across the three elements in the circuit. Show that the potential drop across the LC combination is 0 at the resonant frequency. Now we know the driving condition for resonance is the frequency of the source matches the frequency of the circuit. So that is the main condition of resonance. And at resonance, the inductive reactance is equals to capacitive reactance, and upon rearrangement for omega, there is the angular frequency, we will get the value of omega is equals to 1 by under root the inductance multiplied by capacitance. And at resonance, the impedance is equals to R, because we know the formula for impedance is under root R square plus capacitive reactance minus inductive reactance whole squared. Now when at resonance XC equals XL, this quantity becomes 0, so Z is equals to R. So at resonance, the impedance is equals to R, or Z equals to R. Now current at resonance is given by voltage divided by the impedance or the resistance, and the peak current similarly is defined by the peak voltage divided by the resistance. And potential drop at resonance is given by VR is equals to Im multiplied by R, where Im is the peak current and R is the resistance. Similarly, VL, that is the potential difference, potential drop across the inductor, is equals to Im multiplied by XL, where XL is the inductive reactance. Similarly, the potential drop across the capacitor is equals to Im multiplied by XC, where XC is the capacitive reactance. So we have to calculate the resonant frequency, we have to calculate the impedance of the circuit and the amplitude of current at the resonance frequency, that is Im we have to find out in the second question. We have to find out omega in the first question, and we have to find out potential difference drop across these three components, that is the resistance and capacitor and the inductor. So omega naught, or the resonant frequency, is given by 1 by under root LC. Upon substitution, we will get to know that it is equals to 50 radians per second. And as discussed earlier, at resonance, impedance is equals to resistance, and that will be equal to 40 ohm, because we haven't given that the value of resistor, the resistance of resistor is equals to 40 ohm. So Z will be equal to 40, and the peak current is given by peak voltage divided by R. Now, unless specified, the given potential difference is always the RMS. So for calculating the peak voltage, we will multiply it with root 2. So root 2 multiplied by 230 will be the Vm, or the peak voltage, divided by resistance, that is 40, will give us 8.13 ampere. That is Im, the peak current would be 8.13 ampere. So we have solved this question A and B. Now we have to determine the RMS potential drop across the three elements of the circuit. So we have to find out IRMS for that. So IRMS is equals to peak current divided by root 2, and this will give us 5.75 ampere. So potential drop across the resistor would be equal to IRMS multiplied by R. That will give us 230 volt, because R is 40, and 40 multiplied by 5.75 will give us 230 volt. And VL, that is the potential drop across the inductor, is equals to IRMS multiplied by inductive reactance. This will give us 1437.5 volt. Similarly, the potential drop across the capacitor would be given as IRMS multiplied by capacitive reactance. This will give us 1.37.5 volt again. We have calculated XC as 1 by omega times the capacitance, that is 80 microfarad. 80 microfarad, yes. Now we see that VL is equals to VC. Potential drop across the inductor and the capacitor is equals to 0. Thank you. The question is saying that figure 8.5 shows a capacitor made of two circular plates, each of radius 12 cm and separated by 5 cm distance. The capacitor is being charged by an external source not shown in the figure. The charging current is constant and is equal to 0.15 ampere. Now we have to calculate the capacitance and the rate of change of potential difference between the plates. And we also need to obtain the displacement current across the plates. And the third, we have to tell whether Kirchhoff's first rule or the junction rule is valid at each plate of the capacitor. Now we know that capacitance is defined as C equals to epsilon naught A by D, which depends upon the geometry of the plate. Here we have been given that the radius of each plate is 12 cm and they are separated by 5 cm distance. That is, the radius of this plate is 12 cm and they are separated by 5 cm. We also know that rate of change of potential difference is dV by dt. Now V in terms of the capacitance is defined as Q by C, where Q is the quantity of charge. Now if we differentiate V with respect to T, then we will come to the expression of 1 by C dQ by dt, and we can write dQ by dt as I, that is current. So rate of change of potential difference would be equal to I by C. Now let's find out the expression for displacement current. Now we know that displacement current is defined as epsilon naught d phi E by dt, or the rate of change of flux, and flux is defined as E dot A, the dot product of electric field and the area vector. Now E is defined as sigma by epsilon naught, where sigma is the charge density of the plate, so we can write it as Q by A. Now if we find out flux, then A will get cancelled out. Now flux would be Q by epsilon naught. Now displacement current is defined by epsilon naught d phi by dt. After substituting this flux in this expression, we will get epsilon naught multiplied by dq by epsilon naught. So it would be cancelling the epsilon naught, and we will get the value of displacement current equals to I. So the displacement current would be equal to conduction current. Now let's compute capacitance. Capacitance was epsilon naught A by D. After substituting the area and the displacement and the distance between them, we will come to the conclusion that the capacitance is equals to 8 picofarad. Now computing the rate of change of potential difference dV by dt, we already know from here we have calculated that dV by dt would be equal to current by capacitance. Now substituting that in this expression, we will get a value of 1.87 into 10 to the power 10 volt per second. Now computing displacement current, we already saw from this derivation over here that displacement current would be equal to conduction current. So displacement current would be equal to 0.15 ampere. Now it follows the Kirchhoff's junction rule, as at each plate the conduction current flows into the one side while the displacement current flows out of the other side. The question says that a parallel plate capacitor in figure 8.6 made of circular plates, each of radius 6 cm, has a capacitance C is equals to 100 picofarad. The capacitor is connected to a 230 volt AC supply with an angular frequency of 300 radians per second. Now we have to calculate what is the RMS value of the conduction current, and is the conduction current equal to the displacement current. And in third question, we have to determine the amplitude of B at the point 3 cm from the axis between the plates. Now we know that capacitance is a relationship between the charge and the potential difference across the capacitor, and it is given by C equals to Q by V, where Q is the charge and V is the potential difference. And the conduction current for AC voltages, the RMS conduction current is equal to IC equals to omega C by omega C V RMS. Here it comes from V RMS divided by the impedance XC, and we know that XC is for the capacitor is 1 by omega C. So we will get the conduction current as omega C V RMS, and the peak current is related to the RMS current as I peak equals to root 2 I RMS, and magnetic field at a distance r from the axis between the plate is mu naught I peak r by 2 pi r square, where r is the distance of the point from the axis of the plate, and this capital R is the radius of each circular plate. Let's calculate the conduction current. We have been given the capacitance, that is 100 picofarad, and VRMS is 230 volt, and omega, the angular frequency is 300 radians per second. So RMS current would be equal to IC omega C VRMS. Now substituting in this formula, we will get a value of 6.9 microampere. So the conduction current is going to be equal to 6.9 microampere. Now let's calculate the displacement current. So displacement current arises due to the changing electric field in the capacitor, and Maxwell's equation predict conduction current equals to displacement current. Now since the capacitor is connected to an AC source, the time varying electric field ensures IC equals to ID. So yes, IC is equal to ID here. The conduction current equals the displacement current. Now calculation for the peak magnetic field. Now for calculating the magnetic field amplitude, we will use the peak current. So we will use this formula, mu naught I peak r by 2 pi r square. So substituting the values in this formula, we will get a value of 1.63 into 10 to the power minus 11 Tesla. Thank you. The question is saying that what physical quantity is same for X-rays of wavelength 10 to the power minus 10 meter, red light of wavelength 6800 angstrom, and radio waves of wavelength 500 meter. So basically it is saying that what quantity is same for all these electromagnetic radiations, or what quantity is same for electromagnetic radiations. So electromagnetic radiations has same speed because they all travel with the same speed of approximately 3 into 10 to the power 8 meter per second. Now this constancy arises from the Maxwell equation, which predicts the electromagnetic waves are self-sustaining oscillations of electric and magnetic fields. We also know that C, or the speed of electromagnetic wave, is equals to frequency times lambda. So this speed is going to be same. What changes is wavelength or the frequency. Thank you. The question says that a plane electromagnetic wave travels in vacuum along z direction. What can you say about the direction of electric fields and magnetic field vectors? Is the frequency of wave, if the frequency of wave is 30 megahertz, what is its wavelength? Now we know that electromagnetic waves consist of oscillating electric and magnetic fields that are perpendicular to each other and the direction of the wave propagation. These fields are described by Maxwell's equation, which predict that E and B are perpendicular to each other. Both E and B are perpendicular to the propagation vector k, that is the direction in which wave is propagating, that is in the z direction. So both E and B vector is going to be perpendicular to the z axis or the k cap direction. Now for a wave propagating in z direction, E would be perpendicular to the z and B is also going to be perpendicular to z, and E and B are mutually going to be perpendicular. So you can assume that E is along the x-axis and B is along the y-axis. Now we have to find out the wavelength of the wave whose frequency is going to be 30 megahertz. So the frequency of the wave is given as 30 megahertz or 30 into 10 to the power 6 hertz. The formula for calculating wavelength is the speed divided by frequency. So speed is going to be 3 into 10 to the power 8 meter per second, which is going to be constant, and frequency is 30 megahertz. So after dividing it, we will get a value of 10 meter, that is wavelength is 10 meter. Thank you. The question is saying that a radio can tune into any station in 7.5 megahertz to 12 megahertz band. What is the corresponding wavelength band? So we know that the wavelength can be defined by the speed divided by frequency, and we have to find out here that given the range of frequency, what is the range of wavelength? Wavelength band means the range of wavelength. So here lambda can be calculated by dividing the speed with frequency. So let's calculate. The highest frequency is 12 megahertz and the lowest frequency is 7.5 megahertz. So corresponding with the lowest frequency, there will be the higher wavelength, that is for frequency maximum 12 megahertz. The wavelength is going to be 25 meter, and for the lower frequency, lambda is going to be maximum, that is 40 meter, because lambda equals to c by nu and nu equals to c by lambda. So they both are inversely proportional. So if frequency is maximum, lambda is going to be minimum, and if frequency is minimum, then lambda is going to be maximum. So we come to the conclusion that the wavelength band is going to be 25 meter to 40 meter. Thank you. The question says that a charged particle oscillates about its mean equilibrium position with a frequency of 10 to the power 9 hertz. What is the frequency of electromagnetic waves produced by the oscillator? So we know that accelerated charges radiate electromagnetic waves, and the frequency of the electromagnetic waves equals the frequency of the oscillation of the charge. So we can say that the frequency of the wave produced is identical to the frequency of the oscillating charge, and it is going to be same, that is 10 to the power 9 hertz. So the frequency of the electromagnetic wave produced is going to be of the magnitude 10 to the power 9 hertz. Thank you. The question says that amplitude of magnetic field part of the harmonic electromagnetic wave in vacuum is B naught equals to 510 nanotesla. What is the amplitude of electric field part of the wave? So we know that electric field and magnetic field are related, as electromagnetic wave consists of oscillating electric and magnetic fields. These fields are perpendicular to each other, and they are also perpendicular to the direction of the wave propagation. And the amplitude of the field is given by, they are related by E naught equals to CB naught, that is electric field magnitude is equals to the speed of electromagnetic wave times the magnitude of magnetic field. Now here speed of the electromagnetic wave is 3 into 10 to the power 8 meter per second. Now we have been given the value of B naught, that is the magnitude of magnetic field. We have to find out the value of E naught. So in this formula, only E naught is the unknown. We know the value of C and we know the value of B naught as it is given in the question. So substituting in this formula, we will get a value of E naught, that is the magnitude of electric field, as 153 Newton per Coulomb. Thank you. The question says that suppose that the electric field amplitude of an electromagnetic wave is E naught equals to 120 Newton per Coulomb and its frequency is 50 megahertz. We have to determine the magnitude of magnetic field, omega, angular frequency, k wave number, and the lambda, that is the wavelength. So we know that B naught equals to E naught by C, or the magnetic field magnitude is equals to the electric field magnitude divided by the speed of electromagnetic wave. So upon using this formula, we will get the value of B naught, that is 4 into 10 to the power minus 7 Tesla. For angular frequency, we know that angular frequency is 2 pi by T, or 2 pi nu, or 2 pi into frequency. We haven't given the value of nu, so we can easily calculate angular frequency omega over here, that is 3.14 into 10 to the power 8 radians per second. For wavelength, we know that the formula is the speed of electromagnetic wave divided by the frequency. After substituting the values, we will get the value of 6 meters. So this is the wavelength. For wave number, we know that it is 2 pi by lambda, or the wavelength. So after substituting the values, we will get a value of 1.05 radians per meter. So this is the wave number. Having calculated all these values, we have to now find out the expression for E and B, that is electric field and magnetic field. So we assume that electromagnetic wave is moving in the x direction. So electric field will be along y direction, and the magnetic field will be along z direction. So this is the general expression for the electric field and the magnetic field. Now substituting the values of E naught, that is the peak magnitude of electric field, and k, that is the wave number, and omega, that is the angular frequency, we will get the expression for electric field of this electromagnetic wave. Similarly, substituting the values of corresponding values of the magnetic field, that is the magnetic field magnitude, wave number and all, we will get the value of the expression for magnetic field in this electromagnetic wave. Thank you. The question says that the terminology of different part of electromagnetic spectrum is given in the text. Use the formula E equals to h nu for energy of quantum radiations, photons, and obtain the photon energy in units of electron volt for different part of electromagnetic spectrum. In what way are the different scales of photon energies that you obtain related to the source of electromagnetic radiations? We have to find out photon energy, or the energy of these electromagnetic radiations, and the band is this. For radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays, we have to find out their energy in electron volts, and also we have to find that we have to give a way, we have to tell in what way are the different scale of photon energies that you obtain related to the sources of electromagnetic radiations. So let's start. We know that energy of a photon is given by E equals to h nu, where h is the Planck's constant with the value of 6.63 into 10 to the power minus 34 joules second, and nu is the frequency of the radiation. Now if we relate joule with electron volt, then 1 joule would be equal to 6.242 into 10 to the power 18 electron volt. Now frequency and wavelength are related using this formula, that is C equals to nu times lambda, or we can say that frequency is equals to C by lambda, where C is the speed of the electromagnetic wave and lambda is the wavelength. Now this is the table which represents the electromagnetic spectrum with their wavelength and the energy level. So we can see that as the wavelength is reducing, frequency is increasing and energy is also increasing. We can see that the least energy is of that of the radio waves, which is having a much higher wavelength, much higher than 0.1 meter, and they have frequency of less than 3 into 10 to the power 9 hertz, and they have energy less than 10 to the power minus 5 electron volt. And the gamma rays is having the least wavelength, that is of order of less than 10 to the power minus 11 meter. They are having higher frequencies, 3 into 10 to the power 19, and the energy, they are having the highest energies of 1.24 into 10 to the power 3 electron volt. Now we in this pattern we see that the photon energy increases with frequency and decreases with wavelength, and also we see that higher frequency electromagnetic waves are more penetrative and interact strongly with the matter. Now these kind of these diversity in photon energies allows electromagnetic waves to be utilized in various applications. Thank you. The question says that in a plane electromagnetic wave, electric field oscillates sinusoidally at a frequency of 2 into 10 to the power 10 hertz and the amplitude of 48 volt per meter. Now what is the wavelength of the wave? What is the wavelength of the wave and what is the amplitude of oscillating magnetic field? Show that the average energy density of E, that is electric field, equals the average energy density of magnetic field. we have been given the speed of electromagnetic wave as 3 into 10 to the power 8 meter per second. Now we know that electromagnetic waves consist of oscillating electric and magnetic fields which are perpendicular to each other, and they are also perpendicular to the direction of the wave propagation. Here we have to find out the wavelength of the wave and the amplitude of the oscillating magnetic field, and that is B naught. We have to find here B naught, and we have to find out lambda over here. And we also need to show that the average energy density of E electric field equals the average energy density of magnetic field. So the formula for calculating wavelength is speed of the wave divided by frequency, but before that we should clear some of the facts. The speed of electromagnetic wave in vacuum is 3 into 10 to the power 8 meter per second, and the relationship between electric field and magnetic field is given by B naught, that is the magnetic field is equals to electric field divided by the speed of this electromagnetic wave. Now energy density of electric field and magnetic field is given by the electric field energy density is epsilon naught, the magnitude of electric field square divided by 2. Similarly for magnetic field, the energy density is given by the magnitude of magnetic field square divided by 2 mu naught, where mu naught multiplied with epsilon naught is equals to 1 by c square. So let's calculate the wavelength. The frequency of the wave was 2 into 10 to the power 10 hertz, and the speed of the light was c equals to 3 into 10 to the power 8 meter per second. So for formula for calculating wavelength is c by frequency, that is the speed of the wave by frequency. Now lambda, upon substituting the values over here, we will get a value of 1.5 into 10 to the power minus 2 meter. So the wavelength is going to be equal to 1.5 centimeter. Now let's find the magnitude of magnetic field. So we will use the formula, this formula over here, B naught equals to E naught by C. Electric field amplitude is given as 48 volt per meter, and the speed of light is given as 3 into 10 to the power 8 meter per second. So upon substituting the values over here of E naught and C, we will get a value of B naught, that is the magnitude of magnetic field, as 1.6 into 10 to the power minus 7 Tesla. Now we have to show that the energy density of electric field and magnetic field are same. So we will see the expression for electric field density, that is epsilon naught E square by 2. Similarly for magnetic field it is this. Now using epsilon naught into mu naught equals to 1 by c square, and this the relationship between electric field and magnetic field magnitude, we will come to a conclusion that EB is equals to UE, or the energy density of electric field is equals to energy density of magnetic field. Thank you. The question says that a small candle 2.5 centimeter in size is placed at 27 centimeter in front of a concave mirror of radius of curvature 36 centimeter. At what distance from the mirror should a screen be placed in order to obtain a sharp image, and describe the nature and size of the image? If the candle is moved closer to the mirror, how would the screen have to be moved? So in this question, a concave mirror is given of a defined curvature, radius of curvature, and the object distance from the pole of the mirror is given, that is 27 centimeter, and the height of the object is given, that is 2.5 centimeter in size. At first we have to find out at what position should the screen be placed so that we can obtain the sharp image. So in a simple terms, it is asking the position V of the image from the mirror, and the second question is saying that describe the nature and size of the image, and the third question is if the candle is moved closer to the mirror, how would the screen have to be moved? So the third question is saying that if we move this candle towards the mirror, then how would the position of this image? So let us proceed. So we can use the mirror formula over here, which is given by 1 by f equals to 1 by u plus 1 by v, where f is the focal length and u is the object distance and v is the image distance. So focal length of this mirror is given, that is of 36 centimeter by 2. So we can find out the focal length as 18 centimeter. Object distance is given, since it is in front of the mirror, so u is going to be negative, and it is going to be negative of 27 centimeter. So using this formula, we can calculate the value of v, because only v is unknown over here. So after we get the value of v, we can use it in the formula of magnification. So magnification we will get by minus of v by u, where v is the image distance and u is the object distance. So let's calculate the value of v first. So substituting the values of u and f in this equation, we get the value of v, that is v equals to minus of 54 centimeter. That is, the position of image is in the same side of the mirror as that of the object, because it is negative in size. Now we can negative in magnitude. Now we can calculate the value of m, that is minus of v by u. So substituting the values of v and u in this formula, we will get the value of minus 2, that is, the object is magnified and it is real. We can also see from the image diagram over here. So the at first we have taken the parallel to the principal axis, the array parallel to the principal axis, which is reflected passing through the focus, and the second ray is taken passing through the center of curvature. So it will retrace the incident ray, and since two ray must meet to form an image, so the image will form over here with a value of v equals to minus of 54 centimeter. Now we have got the value of v, that is where should the screen be placed. We have to find out what is the nature and size of the image. So since we have got the value of m, we can find out the we can find out the size of image, that is equals to magnification times the original size of the object, that is 2.5 times 2, that is 5 centimeter, and nature is real, the image is real. And now we have to find out if the candle is moved closer to the mirror, how would the screen have be moved. So that is, if this candle is approaching f and also approaching pole, then how would the position of image be moved. So let us make the diagram over here. So at first case, we assume that the candle has been placed at focus. So we see that these two rays have become parallel. So the image will be forming an infinity. So we can say that if the candle is moved towards the focal length, the position of image will be towards infinity. And if the candle is moved beyond f towards the pole, so we can see that the image is forming, that is virtual. No real image can be formed over here, and it is virtual and it is magnified. Thank you. The question says that a 4.5 centimeter needle is placed 12 centimeter away from the convex mirror of focal length 15 centimeter. Give the location of the image and the magnification. Describe what happens as the needle is moved farther away from the mirror. So here the height of the object is given, that is 4.5 centimeter, and the value of the position away from the mirror is also given, that is of 12 centimeter, and the focal length of the mirror is also given. So we have to find out the location of the image, that is the value of v, and the value of m, that is magnification. So we know from the mirror formula that 1 by f equals to 1 by u plus 1 by v, where f is the focal length and u is the distance of the object from the mirror, and v is the distance of image from the pole of the mirror. And the value of the formula for magnification is minus of v by u. So let us substitute the values. We have been given the value of u, we have been given the value of f. We have to find out the value of v, that is the position of image. So since focal length of convex mirror is positive, so f would be equal to plus of 15 centimeter and u would be equal to minus of 12 centimeter. So finding the unknown v, we will get the value of 6.67 centimeter. Now we have to find out the magnification. So we will substitute the value of u and v in this magnification formula, and we will get the value of equals to plus of 5 by 9. Now let's revisit the ray diagram. Here we have taken two rays from the top of the needle. So one would be along the center of curvature, so it will retrace its incident path, and the another parallel to the principal axis, so it will reflect along the focus of the convex mirror, and if we retrace it behind the mirror, we will get a virtual image. So the nature of image is virtual. The image is diminished because the value of m is less than 1, so the image will be diminished, and the size of image we can calculate with the value of magnification, and the formula is magnification multiplied by original size of the object, and we will get the value of 2.5 centimeter. So we can also see that as the object distance is increased, or as the needle is moved away from the mirror, the image will tend towards the focal point, diminishing in size. Or if we move this object away from this mirror, so this image will move towards the focal point, and the magnification will reduce more and it will become more diminished. Thank you. This question talks about the apparent height and the real height problem. So in this question, there is a beaker and it is filled with water at first, and the height of this beaker is 12.5 centimeter, and at the bottom of the beaker there is a needle, and if you see from the top, then the needle is appearing to be at a depth of 9.4 centimeter. That is the apparent height of this needle is going to be 9.4 centimeter when the beaker is filled with water. We have to find out what is the refractive index of water from the given data. So we have been given the real depth of the tank, that is 12.5 centimeter, and the apparent depth, that is 9.4 centimeter. Now we know that refractive index can be related by real depth and apparent depth, as the refractive index would be equal to real depth by apparent depth. So we have to find out refractive index of water at first. So the real depth is 12.5 centimeter and the apparent depth is 9.4 centimeters. So the refractive index would come out to be 1.33 centimeter. Now the question was saying that when the water is replaced with the fluid of refractive index 1.63, then what would be the apparent depth? And it is not asking directly what is the apparent depth, it is asking by what distance will the microscope move so that it can focus again. So in a nutshell, it is asking what is the apparent depth, what is the new apparent depth. So if we replace the value of refractive index to be 1.63 now in this formula, then we can find out apparent depth, as we have been given the real depth, that is 12.5 centimeter. So apparent depth would be equal to 12.5 centimeter by 1.63. Now if we calculate this, then we can get a value of 7.67 centimeter. So the new apparent depth is going to be 7.67 centimeter if the water is replaced by another liquid. Now this means that the previous apparent depth was 9.4 centimeter as given. Now the new apparent depth is going to be 7.67 centimeter. So the question was asking that what distance should we move the microscope so that it can focus again. So the difference of these two apparent depth is the distance by which we need to move it so that we can focus again. So the difference between 7.67 and 9.4 centimeter is going to be equal to 1.73 centimeter. Thank you. The question says that the figure 9.27 A and B show refraction of a ray in the air incident at 60 degree with a normal to the glass, air and the water air interface respectively. Predict the angle of refraction in glass when the angle of incidence in water is 45 degree with the normal to the water glass interface. Now we have been given two cases of air glass interface and water air interface, and we have to find out what is the angle of refraction in the glass water interface when the ray is incident in the water and going to the glass media. So we will use Snell's law over here. Here for convenience I have taken the refractive index of glass as N1 and refractive index of air as N2 and refractive index of water as N3. Now let's revisit the Snell's law. So it says that when a ray is moving from one media to another, let's say that it is incident in the media of refractive index N1 and it is going in the media of refractive index N2, and it is making an angle of I with the normal in the incident media, and it is going to make an angle of R. So by Snell's law we know that N1 sine I would be equal to N2 sine R. Now we will use this in order to find the alpha, that is the angle of refracted ray in the glass media. So using Snell's law in the first diagram, we see that N1 sine 35 degree is going to be equal to N2 times sine 60 degree. Similarly, equation 2 we will get from the second figure, as N2 sine 60 degree is going to be equal to N3 sine 47 degree. Now similarly we will see here that N1 sine alpha is going to be equal to N3 sine 45 degree. Now solving equation 1 and 2, we will get N1 sine 35 degree is going to be equal to N3 sine 47 degrees. Now we will use this And the third equation to find out the value of sine alpha, because we can cancel out n1 and n3 from these two equations. So by dividing equation 3 by 4, we will get sine alpha by sine 35 degrees is equals to sine 47 degrees by sine 45 degree. Now substituting the values, we will get sine alpha is equals to 0.6 approximately, and now if we take inverse, then we will get a value of 36.8 degrees. So we see that the value of alpha is going to be equal to approximately 36.8 degrees. Thank you. The question says that a small bulb is placed at the bottom of the tank containing water at a depth of 80 centimeter. What is the area of surface of water through which light from the bulb can emerge out? Refractive index of the water is 1.33, and we have to consider the bulb as a point source. Now here we see that it is a water tank. I have symbolized it with the black ink. It is 80 centimeter deep, and in the bottom of the tank there is a bulb which is a point source of light, and we have to find out of what surface area the light will come out. So we will use here the theory of total internal reflection. If we assume there is a ray that is emerging out of the bulb and it is making an angle of I, so in order for that ray to emerge out, it should be less than the critical angle. We know that the critical angle is defined as the angle of incidence, which provides 90 degree to the angle of reflection. That is, if IC is the critical angle, then the refracted ray would not cross the interface and it will just remain on the boundary like this, OA, and the ray will be on the boundary. And if the angle of incidence is greater than critical angle, then the ray will be refracted in the same media. And if it is less than IC or the critical angle, then the ray will come out. Now we have to find out in what area does the ray come out of the tank. Now, since using the Snell's law, we can say that mu of water and sine of I would be equal to, we first will find out the critical angle. So IC will be equal to, let us, the refractive index of the air is 1, so 1 times sine 90 degree. This is 90 degrees, so we will take 90 degree. Now we will find out sine IC. Now this will give us sine IC equal to 1 by 1.33, because we know that mu is 1.33. Now if we figure out what is IC, then IC will be sine inverse 1 by 1.33, and this will come out to be equal to 48.75 degree. So we have got a value of IC in this triangle AOB. We have got the value of IC. Now in order to find out this area, we must know the radius, that is OB, so that we can find out the area. Now radius OB can be found out using the trigonometric relation, that is tan of IC, that tan of IC would be equal to the perpendicular, that is OB, divided by AB. Here we have to find out OB. We know that AB is the height, that is 80 centimeter, which is given. OB would be equal to tan of 48.75 degrees multiplied by AB, that is 80 centimeter, and which will give us something around 91.2 centimeter, that is radius of the circle. Now in order to find out area, we can use the formula of area of circle, that is pi r square, and which will give us 26110 centimeter square, or we can say that 2.61 meter square. The question is saying that a prism is made of a glass of unknown refractive index. A parallel beam of light is incident on the face of the prism. The angle of minimum deviation is measured to be 40 degree. What is the refractive index of the material of the prism? And the refracting angle of the prism is 60 degree. If the prism is placed in water, refractive index of 1.33, predict the new angle of minimum deviation. So here we have been given the value of minimum deviation. Let us symbolize it with dm. We have been given it is the value of 40 degree. we have to find out the refractive index of this prism. And one more thing we have been given, the refracting angle of the prism, that is the vertex angle, it is given as 60 degree. So we can symbolize it with A as 60 degree. Now we know by the definition of the minimum deviation that dm is equals to 2 times I minus A. I is the angle of incidence and it is equals to the angle of emergence for the minimum deviation. We know that the refractive index of the prism is given by sine of A plus dm by 2 divided by sine of A by 2. Now here we have been given the value of A and dm both. So we can simply put it as sine of A plus dm would be equal to 100 by 2, that is 50 degrees, and the value of A is 60 degrees, so it will be equal to sine of 30. Now this will give us a refractive index of 1.53. So we have successfully found out the refractive index of the prism. Now we have to find out what if the prism is placed in water. What will be the new angle of minimum deviation? Refractive index of the prism, that is 1.53. This formula will turn out to be 1.53 by that of the incident media, that is on the water, 1.33. This will give us sine of A. It will be constant because the prism is same, and that is 60 degree, plus dm we have to find out. So dm will be unknown, by 2 divided by sine of A by 2, that is 30 degree. Now after solving this, we will come to a conclusion that dm is equals to 10.32 degree. So here this formula is used. Here the refractive index is refractive index of the prism with respect to the media in which the prism is kept. That's why we use this formula in the case of water, that is the refractive index of prism with respect to media in which the prism is kept. The question is saying that here we have to manufacture a double convex lens from the glass of refractive index of 1.55, and we have been given the focal length that is required, and it is of f equals to 20 centimeter. Since we know the lens maker's formula, we'll be applying it over here. It is saying that we have to make a double convex lens of focal length equal to 20 centimeter. So we know the lens maker's formula, that is 1 by f equals to n minus 1. Here n is the refractive index of the glass with respect to the media in which it is kept, 1 by r1 minus 1 by r2. Here r1 and r2 are the radius of curvature of this side versus this side. Substituting the values, we will get, since it is a convex lens, so focal length is going to be positive. So 1 by 20 would be equal to, refractive index is given, that is 1.55 minus of 1 by r1. Here r1, the radius of curvature is measured from the right hand side because it is curved, and its center would be in the right side. So it is going to be positive. So 1 by r. Since r1 and r2 magnitude is going to be same because it is given over here with the both faces of same radius of curvature. So r1 would be equal to r2 in magnitude minus r2. Since the center of the r2 curvature is going to be on the left hand side, so we will term it as 1 by minus r. Here after solving this, we will get 1 by 20 centimeter is equals to 0.55 multiplied by 2 by r, and this will give us the value of r as 22 centimeter. So the radius of curvature of the glass required is 22 centimeter. Thank you. Beam of light converges at a point P. So let us assume that this is a point P, and a beam of light is converging at this point from the left hand side. And what if we keep concave lens and convex lens? The first is convex lens of focal length 20 centimeter, and the second case we have got a concave lens of focal length 16 centimeters. So here f is equals to plus 20 centimeter, and here f equals to minus of 16 centimeter. Now the distance between these two is 12 centimeter, that is given. So we have to find out where will the beam converge. So in the first case, we will use the lens formula, that is 1 by f equals to 1 by v minus 1 by u. Here object is virtual, that is light was coming to that point, but now it is obstructed, so it is virtual. So 1 by f is equals to, in this case, that is in convex case, 1 by f is going to be 1 by 20. 1 by v, we have to find out 1 by v, and u is 12 centimeter plus or 12 centimeter. So here solving this, we will get a value of 1 by V as 2 by 15 or V as 7.5 centimeter. So what we see here is that, and it is at 7.5 centimeter away from the lens of this convex lens. Now in the second case, we have got a concave lens. Here again, we have to find out the distance, where will the light converge. So here again, we will use the lens formula, that is 1 by V, 1 by F equals to 1 by V minus 1 by U. Now the focal length in the case of concave lens is negative. So we will use 1 by minus of 16 centimeter equals to, we have to find out the image distance, 1 by V minus object, that is virtual, and it is again 12 centimeter away from the pole of the lens. So, and the distance is going to be positive. So we will use 12 centimeter over here. Now solving this, we will get 1 by V is equals to 1 by 48. That is V equals to 48 centimeter. So again, it would be 48 centimeter to the right of the lens. And in the first case, it was 7.5 centimeter to the right of the lens. The question is saying that an object of size 3 centimeter, that is the height of the object is given 3 centimeter, is placed 14 centimeter in front of the concave lens. Here concave lens, the subject is concave lens, and the object distance is 14 centimeters. So we can write u equals to 14 centimeter in front, that is minus for 14 centimeter would be there, and concave lens of focal length 21 centimeters. So here f is going to be equal to minus of 21 centimeter because it is concave lens. Now describe the image produced by the lens. We have to find out image, and we have to describe the image. It means we have to find out V, and we also need to find out M, because that tells us the nature of image, that is whether it is diminished in size and it is virtual or not. So we have to also comment on what happens if the object is moved further away from the lens. Now what if the object is moved, this object is moved away from the lens, or it is moved on the left hand side, what will happen to the image? Now let us first use the lens formula over here. We will find the value of V, then we will find the value of N, and then we will comment on the nature of the image. So using the lens formula, we have got 1 by V minus 1 by U equals to 1 by F. So here 1 by V would be equal to 1 by U, that is 1 by F is minus of 1 by 21 centimeter, and then U will go on that side, and that too is negative, so it will remain negative of 1 by 14 centimeter. This will give us the value of 1 by V equals to minus of 5 by 42. Thus, the value of V is going to be equal to minus of 8.4 centimeter. So the image is on the left hand side of the lens because we have got a value of negative V. Now let us try to find out the value of magnification. Magnification for the lens is defined as V by U. So substituting the values, we will get minus of 8.4 centimeter divided by the value of U is 14 centimeter, minus of 14 centimeter, and this will give us a value of 0.6. So here magnification is less than 1, that is the image will be diminished, and it is positive, magnification is positive. That means the object is going to be virtual and it is going to be erect. Now let us comment on what happens if the object is moved further away from the lens. Now let us first draw roughly the image, the ray diagram of this. So here let us assume that this is the focus. So a ray parallel will go on from here, and then it will appear to diverge from the focus, and the second ray will go from the center. Now the image will be somewhere like this. Now as we move this object away from the focus or away from the lens, let's assume that the object is placed over here. So what we will see is the image will tend towards the focus, because this parallel ray is going to be going in this direction only, but the second ray like this. So we will see that the magnification will drop further on, and as u is increased to infinity, the image distance v will tend towards the focus and the magnification will tend towards 0. Here the question is saying that what is the focal length of the convex lens of focal length 30 centimeter in contact with the concave lens of focal length of 20 centimeter? Is the system converging or diverging lens? Ignore thickness of the lenses. So we have been given thin lenses, and we have to find out what is the effective focal length. Now we know that the effective focal length is given by 1 by f effective is equals to 1 by f1 plus 1 by f2 plus so on. Here we have been given only two lenses, so we will take f1 and f2 only. Now here f1 in the case of convex lens is positive and f2 in the case of concave lens is always negative. So let us calculate the value of f effective, and that is going to be equal to 1 by f1, that is 1 by convex 30 minus of 1 by 20. So after adding this we will get a value of minus of 1 by 60 centimeter. So focal length effective is going to be equal to minus of 60 centimeter. So here we see that the focal length effective is negative. That means it is diverging in nature, or we have got a concave length of focal length 60 centimeter. The question says that a compound microscope consists of an objective lens of focal length 2 centimeter and an eyepiece of focal length 6.25 centimeter separated by a distance of 15 centimeter. How far from the objective should an object be placed in order to obtain the final image at the least distance of the distinct vision, that is 25 centimeter, and at infinity? What is the magnifying power of the microscope in each case? Now here we have been given a compound microscope of which objective has a focal length of 2 centimeter and the eyepiece has a focal length of 6.25 centimeter. We have to find out how far from the objective should an object be placed. Like we have to find out the value of u objective in the case VE, that is the image formed by the eyepiece is at minus t. D is the least distance of distinct vision, that is 25 centimeter, and the second case is at VE is equals to infinity, that is the image is forming at infinity, which is good for relaxed eye view. Now we have to also find out what is the magnifying power of microscope in each case. We have to also find out the value of m. Now we will use two formulas in this question. The first is lens formula, that is 1 by v minus 1 by u equals to 1 by f. Here I have represented v, fe and fo as a focal length of eyepiece and the objective respectively, and subsequently u and v has been also represented with the subscript of e and o, as e as the eyepiece and o as the objective. Now let us move towards the first case where the image is forming at the least distance of distinct vision, that is 25 centimeter. So we know that in a compound microscope an object is placed over here in front of objective. Now this will form a virtual image between these two lenses, let us say over here, and this virtual image will be treated as a virtual object for eyepiece, and this eyepiece will form the final image, which is somewhere magnified. Now we have to find out the value of u naught in both the cases. So in the first case, the least distance of distinct vision, the image is forming, that is the final image, VE is forming at minus d. So we will use the lens formula for the eyepiece. We have been given the value of VE over here, that is minus of d, that is minus of 25 centimeter. So using the lens formula for the eyepiece, we have got 1 by VE minus 1 by UE is equals to 1 by FE. So d here 1 by V is minus of 25 centimeter. Now 1 by UE is equals to 1 by 6.25. We have been given the value of FE, that is 6.25. And since it is a convex lens, so FE is going to be positive. Now solving for this, we have got a value of UE as minus of 5 centimeter. So it means that the object for the eyepiece should be at minus of 5 centimeter, or with proper sign convention, the object should be here with a distance of 5 centimeter from this pole of this lens, that is 5 centimeter. Now for the image to form at minus d, the object should be here. Now for this lens, what is the distance between this lens and this image? So the image by the objective is going to be treated as the object for this eyepiece. So if the object should be at here, that is at 5 centimeter from the left of the lens, then the image formed by the objective should be at 10 centimeter on the right side of this lens. So V naught, that is the image distance for this objective, should be equal to 10 centimeter. So V naught or the VO is equals to 15 centimeter minus 5 centimeter, that is 10 centimeter. So we have got a value of FO. We have been given the value of FO, that is the focal length of the objective, that is 2 centimeter. We have to find out the value of UO, that is the object distance from the objective. So using lens formula again, we have been given the value of FO and VO, and we have to find out the value of UO. So solving this, we have got a value of U as minus 2.5 centimeter. So the solution of first case is here, that is if the object is kept at 2 centimeter from the lens of the from the left of the objective, then we will get a final image at a distance of 25 centimeter from the left of this eyepiece. Now we have to find out the value of magnification. So magnification in this case, we know the formula for magnification is it is given by VO by UO multiplied by D by UE. So here VO is the image distance from the objective and UO is the object distance from the objective. D is the distance of distinct vision and UE is the object distance from the eyepiece. So we have all the values over here. We will substitute it and we will get a value of 20x. So when the image is forming at the least distance of distinct vision, then we are getting a magnification power of 20. Now in the second case, the question was final image at infinity. That is, the final image formed by this eyepiece is going to be at infinity. So we know for image to form at infinity, the object will place at the focus. So UE, that is object for the eyepiece, is going to be minus FE, and we have been given the value of FE, that is 6.25 centimeter. Focal length of the eyepiece, that is 6.25 centimeter. So let us find out the distance of VO. Distance between the two lenses is 15 centimeter. So VO plus UE, that is, let us understand with this diagram. VO plus UE. VO is the image formed by the objective. VO is the image formed by the objective plus UE, that is, that image is going to be the object for the eyepiece. This will always be equal to 15 centimeter because the distance between the lens is fixed, 15 centimeter. So using this, we will find out the value of VO, that is the image distance from the objective, and this will give us a value of 15 minus 6.25, that is 8.75. Since this is from the right of the objective, so this will be positive. We will put it in the lens equation again, and for finding out the value of UO, so for solving this question, we will get the value of UO as minus of 2.59 centimeter. Now we have got the data for the second case as well, that is when the image is forming at infinity. So using the formula, same formula for magnification, that is VO by UO into D by UE, we will get a value of magnification as 13.51 x. That is, the magnifying power is less when the image is forming at infinity as compared to when the image is forming at the least distance of distinct vision, that is 25 centimeter. I hope you understood this question. The question says that a person with normal near point 25 centimeter using a compound microscope with objective of focal length 8 millimeter and eyepiece of focal length 2.5 centimeter can bring an object placed at 9 millimeter from the objective in a sharp focus. What is the separation between the two lenses? Calculate the magnifying power of the microscope. So in this question, it is simply asking that what would be the distance between these two lenses such that if object is placed at 9 millimeter or 0.9 centimeter in front of the object, the person with a normal near point of 25 centimeter sees that object clearly. So it is simply asking what would be the length between, what would be the distance between these two lenses such that the person can focus it, or the eyepiece can create an image at V equals to 25 centimeter in front of it. So in order to get the length between these two lenses, we will have to find out the distance between the image created by the objective, that is V naught, and the distance between the image and that eyepiece lens, or we can term it as object length UE. So length will be composed of V0, that is the image distance between the objective lens and the image, and UE, that is the object distance from the eyepiece. That will give us the answer. Now we have to also calculate the magnifying power of the microscope. So in order to find out V0, VO and UE, we will use the lens equation. So we know that using the lens equation on the objective, we know that 1 by V0 minus 1 by U0 is equals to 1 by focal length of that objective. Now using these values that are given for VO, that is 9 millimeter, we will use it as minus 1 by 0.9. So we will get V0 as 36.5 centimeter. Now what is left is calculation of UE, that is the object distance between the eyepiece and the image formed by the objective. So using the lens formula again on the eyepiece, we know the value of VE, that is the image must form at the least distance of distinct vision, that is 25 centimeter in front of the eyepiece, and we have been given the focal length of the objective, that is 2.5 centimeter, focal length of the eyepiece, that is 2.5 centimeter. So we only need to find UE. So upon calculation, we will get a UE is equals to minus of 25 by 11. Now the length, as we saw earlier, would be composed of V0 plus UE, the magnitude of these two values. So after adding these two values, we will get a distance of 9.47. That is, the length of the microscope would be 9.47 for the clear vision. Thank you. We also need to find the magnification in this case. So magnification is given by VO by UO into D by UE. So we know the value of VO over here. We have calculated it as 36.5, and UO is given, that is 0.9. Distance of the object from the objective. D is known, that is 25 centimeter, and UE we calculated to a value of 25 by 11. So after this formula, using this formula and substituting the values, we will get a result of 88. That is, the magnification of this microscope is 88x. The question is saying that a small telescope has an objective lens of focal length 144 centimeter and an eyepiece of focal length 6 centimeter. What is the magnifying power of the telescope? What is the separation between the objective and the eyepiece? So in a telescope, we know that for the image to be forming at the infinity, image formed by objective must lie on the first focus of the eyepiece. That is, if image formed by this lens is on the focal point of the of the eyepiece, then the image will be formed at infinity. That is, the total length of this telescope would be given by focal length of the objective plus focal length of the eyepiece. Now here, since the rays are approaching from the infinity, so we assume that the image is formed at the focus of the objective, the second focal point of the objective, and that image will be used as a virtual object for this eyepiece to form the image, to form the final image. Now, magnifying power is given by focal length of the objective by focal length of the eyepiece, and substituting the values of 144 and 6 centimeter, we will get a value of 24x. That is, the magnifying power of this microscope is 24x. And the question about the separation between the objective and the eyepiece. So we know, or we saw earlier, that the separation is given by the addition of these two focal lengths. So it will be 144 plus 6 centimeter, which will give out to be value of 150 centimeter. Thank you. The question says that a giant refracting telescope at an observatory has an objective lens of focal length 15 meter. If an eyepiece of focal length 1 centimeter is used, what is the angular magnification of the telescope? The second question says that if the telescope is used to view the moon, what is the diameter of the image of the moon formed by the objective lens? The diameter of the moon is 3.48 into 10 to the power 6 meter, and the radius of the lunar orbit is 3.8 into 10 to the power 6 meters. So first question is saying that simply we have to find out the magnification of this telescope. So we know the formula for magnification. It is given by the focal length of the objective by focal length of the eyepiece. So after substituting the values, we will get a value of 1500x. Now the second question is asking what would be the diameter of the image of the moon given the radius of the given the diameter of the actual moon and the distance of moon between earth, that is the lunar orbit or the orbit in which moon rotates around the earth, that is 3.8 into 10 to the power 6 meter. So here let us revisit the ray diagram formed by the convex lenses. So if we see that an object is beyond the focal length, then height of the object is HO and height of the image is HI. So if we focus, so these are the two rays that I have shown over here. The first rays is parallel to the focus, parallel to the principal axis, so it will go from focus to the beyond, and then the second rays towards the pole of the lens, so it will go unaltered, and the intersection will form the image. So if we focus on the two triangles over here, that is OAB and OCD, these two triangles are always going to be similar. And we know the property of similar triangle is that the ratio of the similar sides are always equal. So in this two triangle, OAB and OCD, OA by OC will always be equal to AB by CD. So this question was asking what is the radius of the moon of the image? What is the radius of the image of the moon? So if we substitute the values, if we assume that this is the moon over here, now this is going to be the radius of the moon. So we can assume that AB is the radius of the moon and OA is the distance of the moon from the earth, that is the lunar orbit, and OC is the focal length of the objective. OC is the focal length of the objective, and CD is the radius of the image. So hi is the radius of the image. So moon will be forming like this. So we can assume like this condition. And from the property of the similar triangles, using this ratio, we can easily calculate the value of CD, that is unknown over here, that is the radius of the image of the moon. So substituting the values, we will get CD equals to 6.86 into 10 to the power 2 meter. We will get a value of 6.86 into 10 to the power minus 2 meter. So we can easily calculate the diameter of the moon now. So diameter of the moon would be equal to 2 times CD, that is 13.7 centimeter. Thank you. The question says that use the mirror equation to deduce that an object placed between f and 2f of a concave mirror produces a real image beyond 2f. Now there are four similar given questions, and in each question we have to use the mirror equation to deduce the following statements. So let's continue one by one. So in the first statement, we have been given an object placed between f and 2f of a concave mirror produces a real image beyond 2f. So here is a concave mirror, and we have to use this mirror equation. We don't need to rely on the mirror on the ray diagram. I have just used the ray diagram for the illustration. So we have to prove that when the object is placed between f and 2f, that is f and 2f, the concave mirror produces a real image beyond 2f. The image will be produced beyond 2f and it will be real. That is, it will be formed by the real intersection of light, or in a simple term, it should be formed on the left side of the mirror. That is, V should be negative. V, that is the distance from the pole of the mirror to the image, should be negative using the sign convention. So let's begin. I have assumed that the distance between the focus and the object is x. That's making u, that is the object distance from the pole of the mirror, would be equal to f plus x. Now using the sign convention, u can be substituted as minus of f by f plus x. So using this value in the mirror equation, we will get 1 by v, that is the image distance, minus 1 by f plus x equal to minus of 1 by f. Here minus is because the concave mirror, its focal length using sign convention is taken negative. So 1 by v would be equal to minus of 1 by f plus 1 by f plus x. Now using simplifying this, we will get the value of v as f multiplied by f plus x by x minus of f multiplied by f plus x by x. Now in the question, it was an object placed between f and af, f and 2f. That is, when the object is at f, x would be equal to 0. So using this x equal to 0 in this expression, we will get a value of minus infinity, that is v tend to minus infinity. And when object is at 2f, x will be equal to f. Using the value of f in the place of x, we will get a value of minus of 2x. So in this expression, we see that the image lies between minus of infinity to minus of 2f. Thus, the image is real as it is forming by the real intersection of the rays. And in the question also, it was given that we have to prove that when the object is placed between f and 2f of the concave mirror, then it produces a real image beyond 2f. And the image is also beyond 2f. The second question was, a concave mirror produces a virtual image independent of the location of the object. So a convex mirror produces, the question B was, a convex mirror always produces virtual image independent of the location of the object. So here we have been given a convex mirror, and we have to prove that it will always produce virtual image irrespective of the position of the object. So here I have assumed again u, the magnitude of u as x. So using sign convention, we can write u as minus x. Substituting in this mirror equation, we will get 1 by v minus 1 by x equals to 1 by f. Here f is positive because it is a convex mirror. And simplifying this, we will get the expression for v, that is fx by f plus x. Here we see that for x equals to 0, v is always equals to 0. That is, wherever the object is placed, that is x equals to 0, the v is always going to be positive. The image is always forming on the other side of the mirror, or the image is always virtual. Since v is positive, it means that v measured from here is always going to be in this side of the mirror, that is in the right side of the mirror. Thus there will always be a virtual image forming for this case. Now the third question was, the virtual image produced by a convex mirror is always diminished in size and located between focus and the pole. So the question is asking us to comment on the magnification, and it is also asking us to comment on the position of the image that is lying between the pole and the focus. So from the above calculation for V, we see that V is equals to fx by f plus x, and if we divide both the terms, both the numerator and denominator by x, we will get f by x plus 1. So when we increase the value of x over here, then we see that this term is going to be 0. This term will tend towards 0. Thus the maximum value of v that we can achieve would be v equals to f. That is, if we increase the value of x, then v will approach to f. That is, if we take the image away from the mirror, if we take the object away from the mirror, then the maximum position of the image is going to be at f. That's what the question said. Now we have to comment on the magnification in this case. Now magnification, we know that it is given by minus of v by u. So we will substitute it in the given formula, that is minus of v fx by f plus x into minus into 1 by u, that is 1 by minus x. So equating this, we will get f by f plus x. Now here we see that as x increases, f by f plus x is always going to be less than 1. That is, the object, that is, the image will always be diminished. And m is always going to be positive, that is, the virtual image will always be erect. Now let's focus towards the last question. Last question said that the object placed between pole and the focus of the concave mirror produces a virtual and enlarged image. Virtual and enlarged image. We have to prove that. So let's assume that the distance between the object and the pole of the mirror is x. Now using sign convention, we can write u as minus of x, and I have substituted it in the mirror equation, 1 by v plus 1 by u equals to 1 by f. So 1 by v minus 1 by x equals to minus of f, because it is a concave mirror. Now again, solving for v, we will get the value of v as fx by f minus x. So now for u equals to minus f x equals to f, that is, using this value of x in this expression, we will get the value of v as infinity. That is, when the object is at focus, the image will be at infinity. Now, for the case when u is between f and 0, or the object is between focus and the pole, we will get a value of v as positive, because x will always be less than focus in magnitude. Thus, this both term is going to be positive. Thus, v is going to be positive. And what it means that v is positive? We see that if v is positive, the mirror will always form the image in the right side of the mirror. That's why we can say that the image will always be virtual. Now let's comment on the magnification. So substituting the values of v and u in the magnification formula, we will get the value of m as f by f minus x. Now since f minus x will always be less than f, thus the value of m will always be greater than 1. Now here you should mark that I have used the sign convention for x over here. So x will always be positive over here. So that is why f minus x will always be less than f. So m will always be greater than 1, or the image will always be enlarged. That's how we have proved all those 4 statements that were given using the mirror formula. Thank you. The question is saying that a small pin fixed on a tabletop is viewed from above from a distance of 50 centimeter. By what distance would the pin appear to be raised if it is viewed from the same point through the 15 centimeter thick glass slab held parallel to the table? Refractive index of glass is 1.5 centimeter, 1.5. And does this answer depend on the location of the slab? So here there is a pinpoint on the slab, pinpoint on the table, and there is a slab through which an eye is there, or a person observer is there, and it is viewing the pin top. Now we have to find out by what distance will this top be appear elevated. Like, since the actual distance is 50 centimeter, then by what distance will it appear elevated because of this glass? So we know the formula for apparent depth or apparent length in this case, because the light is traveling from a different media, so there will be apparent shift. Now length apparent would be given by d1, that is the thickness of the glass, divided by mu1, that is the refractive index of this glass. Now substituting the values, we will get apparent depth of 10 centimeter. What means is that though the thickness of glass is 15 centimeter, but it would appear as if it is just 10 centimeter. So there will be a shift of 15 minus 10 equals to 5 centimeter, or the pin top will appear to be have moved 5 centimeter above. So we can say that the pin appears not to be at 15 centimeter as the thickness of the block rather than 10 centimeter. So the pin appears to be raised by 5 centimeter. The question is saying that figure 9.28 shows a cross section of light pipe made of a glass fiber of refractive index 1.68. The outer covering of the pipe is made of material of refractive index 1.44. What is the range of the angle of incident rays with the axis of pipe for which the total internal reflection inside the pipe take place, as shown in the figure? What is the answer if there is no outer covering of the pipe? So this is a glass pipe in which ray of light is traveling. Now we have been given that this is the angle of incidence by which the ray enters, and this is the angle of refraction, first refraction, and we have to find out the condition over which what would be the angle of incidence for which total internal reflection takes place. That is, the light doesn't pass through the outer covering, it reflects totally inside. What is the criteria for total internal reflection for this interface, that is the outer covering and the glass interface? Now we can apply Snell's law over here. Now this is the first part of the question, like we have to find out what is the range of I, this I. Now the second part of the question says that what if we remove this outer covering, then we have to find out the range of I. So we will be using Snell's law over here. Now let's revisit the Snell's law. So it says that if the angle of incidence in one media of refractive index n1 and the angle of refraction in the other media of refractive index n2, then it can be related by n1 sin I equals to n2 sin R. So we will use this Snell's law in order to find out the critical angle. So let's calculate the critical angle. So using this Snell's law over this diagram, we can say that we can see that sin IC equals to sin inverse mu2 by mu1, where mu2 is the refractive index of the glass outer covering and mu1 is the refractive index of the inner core of the glass. Now this will give us IC as 59 degree, that is critical angle of 59 degree. So by now we have come to know that IC, that is I dash must be at least 59 degree for the total internal reflection to take place. Now the minimum value of I dash is 59 degree. So in this triangle we can easily find out what should be the value of R so that total internal reflection takes place. That is, if this angle is 59 degree, then what would be the value of R? So we know that this is a right angle triangle. So I dash plus R must be equal to 90 degree. So R plus 59 degree must be equal to 90 degree. So the value of R must be equal to 31 degree. So the minimum value of I dash should be 59 degree. So maximum value of R should be 31 degree. Now for this value of R to be 31 degree, what should be the angle of incidence? Again we will apply Snell's law over here. Now we can take the refractive index of this media as 1, and we know the refractive index of this media, that is the glass core media, as 1.68. So we will apply Snell's law over here. So calculating the condition for R that is less than 31 degree would be 1 sin I is equals to 1.68 sin R. Now sin I by sin 31 degree, that is sin R, I have written sin 31 degree, would be equal to 1.68. Now this will give us sin I equals to 1.68 times 0.52. Now 0.52 is the value of sin 31 degree. I have substituted it over there. Now the value of I would be equal to approximately 60 degree. That is, for the angle of incidence of 60 degree, we will get a value of angle of refraction in the glass core as 31 degree. Now the angle of refraction must be less than 31 degree in order for the total internal reflection to take place. Now if we increase this value of I, then obviously the angle of refraction will also increase. So the angle of incidence must be less than 60 degrees so that the angle of refraction doesn't surpass 31 degree, or the IC or I dash, the value of I dash shouldn't decrease from the critical angle, because if the value of I dash will decrease from the critical angle, then the total internal reflection will not take place. Now we have found out the condition for total internal reflection to take place, that is I should be less than 60 degree and greater than 0. Now let's cover the case when there is no any outer covering. Now in this case, we can assume that mu2, that is the value of outer covering, refractive index of outer covering, mu2 is equals to 1. Now in this case, we will see that again we will find out the value of IC using the Snell's law. So we can write over here that I1 sin IC equals to mu1 sin IC equals to mu2 sin R. Now R is the angle of refraction over here and IC is this one. So substituting the values of refractive index, we will get 1.68 into sin IC is equals to sin 90 degree. R is 90 degree over here. So we will get a value of IC as 36.5 degree. Now for total internal reflection, we saw that since IC is equals to 36.5 degrees, so I dash must be greater than this critical angle, that is 36.5 degree. Now again, using this triangle, we can see that if the minimum value of I dash is equals to 36.5 degree, so the maximum value of R should be 90 minus 36.5 degree. That will give us a value of 53.5 degree. So maximum value of R should be 36.5 degree. Now we saw in this case that since this media and this outer covering apart from the glass core media is same with refractive index of 1, so we saw that for this angle IC, automatically the angle of refraction is getting 90 degree. So we can conversely say that I is equals to 90 degree for R is equals to 36.5 degree. Now the value of R is 36.5 degrees. So this value will never cross the maximum permissible value for any given value of I. So we can say that for every value of I, the total internal reflection will take place. The question says that the image of a small electric bulb fixed on a wall of a room is to be obtained on the opposite wall 3 meters away by the means of large convex lens. What is the maximum possible focal length of the lens required for the purpose? Now, in this diagram, we see there is a electric bulb on a wall and there is a convex lens which will be used to cast an image of this bulb on that screen or the wall. And the distance between this wall that is carrying the bulb and the screen is 3 meters. Now this distance is fixed. We have to find out what would be the maximum focal length for which we can cast the image on that screen. So here we will use the lens equation. So for maximum focal length, we will solve for f maximum. Now we have assumed u to be x variable, that is distance of the object or the bulb or the wall that is carrying the bulb from the lens as u equal to x. Now obviously the image distance will be 3 minus x because it is fixed. The distance between those two walls is fixed. Now using the sign convention and the lens formula and substituting the values in this equation, we will see that 1 by v becomes 3 minus x, and since the screen is on the right hand side, it is going to be positive, so it would be 3 minus x minus u is on the left side of this lens, so it is going to be negative. So I have substituted 1 by minus x equals to 1 by f. So using the values u equals to x and v equals to 3 minus x, we have substituted the values over here in this lens equation. Now solving for f, we get a value of f as 3x times 3 minus x by 3. Now upon simplification, we will get f as x minus x square by 3. Now for fx to be maximum, for this focal length function to be maximum, we know the mathematical condition, that is this one, f dash x, or the differentiation of the function of focal length with respect to x must be equal to 0, and the double differentiation of that function with respect to x must be less than 0. Now differentiating it for the first time with respect to x and equating it with 0, we came to the conclusion that the value of x is 3 by 2 or 1.5 meter. Now checking it for the double differentiation, we get the negative, that is for the value of x as 3 by 2, fx is going to be negative, fx is going to be minimum. Now since we know that we have used as 3 minus x and we have got the value of x, that is u, so we have got the value of u and v as u equals to 1.5 meter and v as well as 1.5 meter. Now using those values in the lens equation with proper sign convention, we come to the conclusion that 1 by f is equals to 1 by 1.5 minus of 1 by 1.5. Now upon calculation, we will get the value of focal length as 75 centimeter. The question says that a screen is placed 90 centimeter from an object The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeters. Determine the focal length of the lens. So we have been given an object and a screen and the distance of separation between them, that is 90 centimeter, and we have to find out what would be the focal length of this lens, given that there are two images, there are two positions for this lens where the image can be casted on this screen, and those positions are separated by a distance of 20 centimeter. So let us represent it by d. The position of the difference between the position of the lenses which can subtend the image on the screen. So let us assume that the first position, the distance of the object from the lens from the first position is u1, and the distance of the object from the second position is u2, and subsequently the image distance would be v1 and v2. Now we know that since this distance from the object and the screen is fixed, and that is 90 centimeters, so u1 plus v1 or u2 plus v2 equals. Now using these relations, we have to find out the value of focal length of the lens. Now let us generalize this approach by saying the distance between the object and the lens wherever it is, either in the first position or in the second position, be x variable. So automatically the image distance from the lens would be 90 minus x, because the total distance is 90 centimeters. So v would be equal to 90 minus x. Now let us use the lens formula over here. That is 1 by v minus 1 by u equals to 1 by f. With proper sign convention, we can write 1 by 90 minus x, that is v. Since v is in the right side of the lens, so it is going to be positive, and u, that is the object, is in the left side of the lens, so it is going to be negative. So 1 by 90 minus x minus of 1 by x equals to 1 by f. Since it is a convex lens, so focal length is going to be positive. Now simplifying this, we get the relation for focal length as 90 minus x times x by 90. Now for quadratic equation, so this is a form of quadratic equation which can be further simplified to is this x square minus 90x plus 90f equals to 0. Now in this equation there are two variables, x and f. So let us first take a look at the quadratic equation solutions. So for a quadratic equation ax square plus bx plus c, we know that the solutions are given by minus of b plus minus root under b square minus 4ac by 2a. So using this coefficients, we can write the solution for this equation as well, as x equals to minus of 90 plus minus under root minus of 90 whole square minus 4 times 1 times 90f by 2. So one solution will contain plus of this determinant, and another solution will contain minus of this determinant. We know that x is the solution for the value of u, that is the distance between the object and the lens. So we also know that the difference of this position that we have taken earlier, that is u2 minus u1, would be equal to d, that is this distance of separation, that is 20 centimeter. So we can simply write over here, then u2 minus u1 is equals to 20 centimeter, or the first solution minus the second solution is equals to 20 centimeter, or we can say that the distance of the first solution minus the distance of second solution is equals to 20 centimeter. Let us use this relation to eliminate one of the variables among x and f. So we can write that u2 minus u1 equals to d, that is 20 centimeter, or we can say that the distance without any sign convention, we can write it as x2 minus x1 equals to d. So using this and substituting the values of the two solutions of x, we come to a value of 20 under root of 90 square minus 4 times 90f is equals to 20. Now squaring both the sides of this equation, we will get the value of f as 21.4 centimeter. That's how we have found out the value of x. That's how we have found out the value of f, that is the focal length of convex lens. The question says that determine the effective focal length of the combination of the two lenses in exercise 9.10 if they are placed 8 centimeter apart with their principal axis coincident. Does the answer depend on which side of the combination a beam of parallel light is incident? Is the notion of effective focal length of this system useful at all? So in the previous exercise of 9.10, we were given two lenses, a convex lens and a concave lens, and we were asked to find the f effective or the net focal length of the system. Now in this question, it is asking that these two lenses are kept apart 8 centimeter. Now we have to find out what would be the effective focal length, and does that hold any meaning at all? Here we have to determine the effective focal length of the combination of the two lenses, and we also need to answer that will the effective focal length depend on which side of the lens the light is coming from, or which side of the lens the object is placed. And we also need to comment, is the notion of effective focal length of the system useful at all? Now, here we can make two cases to find out whether the answer will depend on which side of the combination of the beam of parallel light is incident. We will first put concave lens on the back side of the convex lens, or if we imagine the rays coming from an object that is placed at infinite, or the rays are parallel. So at first we will put the convex lens on the left hand side, and then in the second case we will put concave lens on the left hand side and see will the answer depend. Now for an object at infinity, on the left hand side the image will form at the focus of the convex lens. Since we have been given the focus of 30 centimeter, so the distance of image from for this lens would be v equals to 30 centimeter. As u1 is infinity, u1 as in the case of convex lens, that is the first lens, we can say that v1 is equals to 30 centimeter, and u2 here represents the object distance for the concave lens, that is the second lens. When this lens is forming the image, it would be 30 centimeter on the right hand side of the lens. So 30 centimeter from this direction would be somewhere here. Now the distance of this image which will act as an object for this concave lens will be 30 minus 8, that will be equal to 22 centimeter. So for this lens, the object will be placed at 22 centimeter on the right hand side. So we can write U2 as 22 centimeter. Now using the lens formula for this second lens, we can find out the value of its V, that is the image formation, the position of the image. So using this lens formula for this concave lens, we can write 1 by V equals to 1 by F plus 1 by U, and 1 by U is 1 by 22 centimeter, and 1 by f is 1 by minus of 20 centimeter, because the focal length is given as 20 centimeter, and since it is a concave lens we can write it as minus 20. So calculating this, we will get a value of v as minus 220 centimeter. So for this lens arrangement, we will get, when the object is at infinity, the final image will be forming at v equals to minus of 220 centimeter on the left hand side of this lens by a distance of minus of 220 centimeter. Now we will consider the second case in which concave lens is the first lens and the convex lens is the second lens. So here v1 would be equals to minus of f, because when the incident ray is there, it will virtually tend to form an image in front of the concave lens 20 centimeter or equals to its focal length. Now we can treat this image as a virtual object for this convex lens. So u2 would be equal to this 20 centimeter plus of this 8 centimeter distance. So the total value of u2 would be minus of 28 centimeter with sign convention. So again applying lens formula over here. So we will get 1 by v equals to 1 by f plus 1 by u, and we saw that 1 by u is equals to 1 by minus of 28 centimeter, and since focal length is positive for the convex lens, so it will be 1 by 30. Calculating this, we will get a value of v as minus of 420 centimeter. Now we can comment that seeing this results that v changed from the previous case of 220 centimeters, so that we can say that yes, the answer depend on which side the incident ray is coming from, because v has changed or the final image distance has changed. And we can also comment that no, the notion of effective focal length won't work in this case, because there can't be f effective, as the image position is varying depending upon which side or which lens is receiving the first incident rays. Now the second question asked, like, an object of 1.5 centimeter is placed on the side of the convex lens in arrangement A above. The distance between the object and the convex lens is 40 centimeter. Determine the magnification produced by the two lens system and the size of the image. So now using this arrangement, we have been given the value of u, that is the object distance from the convex lens, and that is of 40 centimeter, and the object size or the height of object is given, that is 1.5 centimeter. and we have to find out what is the magnification produced by the two lens system, and also we have to determine the size of the image. So let's go to the calculation. So this is the arrangement that we were talking about. The object is placed in front of convex lens and u has been given, and that is a value of minus of 40 centimeter. Focal length of this convex lens is 30 centimeter, and focal length of this concave lens is minus 20 centimeter, and the distance between these two lenses is again 8 centimeter. So we will consider this first lens and this as the second lens. So u1 would be equal to minus of 40 centimeter with the sign convention. So using lens formula for finding out the image produced by this convex lens, so 1 by v equal to minus of 1 by u, and that is u is minus of 40. So 1 by v equals to minus of 1 by 40, and that would equal to focal length. Focal length of convex lens is positive, so it will be equal to 1 of 1 by 30. So calculating here v, we will get a value of 120 centimeter. Now we can see that from the pole of this lens, the image will form, the first image will form 1 centimeter on the right hand side of this lens. So this image will act as an object for this concave lens. So we can find out the object length, object distance from for this concave lens, and that would be equal to u2 would be equal to this 120 centimeter minus of this distance 8 centimeter, and that will come out to be equal to 112 centimeter. Since this distance is on the right hand side of the concave lens, so it is going to be positive, or u2 is going to be plus of 112 centimeter. Now applying the lens law over here, 1 by v minus 1 by equals to 1 by f. Here f is negative because it is a concave lens, and 1 by v minus 1 by 112 would be equal to minus of 1 by 20. So solving this for v, we will get a value of v as minus of 560 by 23 centimeter. That is, the position of image is on the left hand side of this concave lens at minus of 560 by 23 centimeter on the left hand side of this concave lens. So we have got this value of u1, v1 and u1, and v2 and u2. Now we can find out the magnification of each lens independently, and then we can find out the product of magnification so that we can get the net magnification. So magnification for the convex lens would be equal to m1 equals to 120 by minus of 40, as m is equals to v upon u. So we can divide it and get the value of magnification by the first lens as minus of 3, and by second lens similarly we will substitute the values in that formula, in this formula, and we will get the value of minus of 5 by 23. Now net magnification will be equal to the product of these two independent magnifications, and that will be equal to 0.652. That is, the net magnification is less than 1 and it is diminished in size. So the final height of this image is going to be equal to net magnification multiplied by the original height, and that we will get solution as 0.98 centimeter, because the initial height was 1.5 centimeter. So we can multiply it with 0.652. That is a net magnification, and we will get the value as 0.98 centimeter. The question says that at what angle should a ray of light be incident on the face of a prism of refraction angle 60 degrees so that it suffers total internal reflection at the other face? The refractive index of the material of the prism is 1.524. So here we are being talked about the faces of prism A, B, C, and the faces that are in consideration are AB and AC. Now on the face AB, the incident ray ON makes an angle I of incidence with the normal, and it goes in the prism with the angle of refraction equals to R1. Now it strikes the second face AC with an angle of incidence of R2, and it goes out with an angle of refraction as E, or angle of emergence. Now in our question it is said that on the second face it should reflect such that total internal reflection happens, or the angle of emergence should be equal to 90 degrees. So for that condition we have to find out what would be the value of I. So we know in a prism the angle between two faces are called the angle of refraction. The prism and it is given over here that it is 60 degree. So we also know the relation for prism that R1 plus R2, this R1 plus this R2 is equals to the angle of refraction of the prism, the angle between the two faces, and that would be equal to 60 degree over here. So R1 plus R2 equals to 60 degree. Now we will be applying Snell's law on these two faces AB and AC. So applying Snell's law on face AB, it would be equal to, if the outer media is having refractive index of mu1 and the prism is having refractive index of mu2, then it would be equal to mu1 sine I is equals to mu2 sine R1. So we can say that the mu1 or the refractive index of the media surrounding the prism is 1, and sine I would be equal to 1.524 times sine R1. Now applying Snell's law on the interface AC, that is the second phase, we could see that it is mu2 sine R2 equals to N1 sine E. N1 is the refractive index of the media that is surrounding the prism. Now for total internal reflection, as we discussed, E would be equal to 90 degree. So substituting the value, we will get sine R2 equals to 1 by 1.524. Now R2 would be equal to sine inverse of 1 by 1.524. This will give us R2 the value of 41 degree. Now substituting this value R2 equals to 41 degree in equation number 1, that was R1 plus R2 equals to 60 degree. We will get the value of R1 as 19 degree. Now substituting this value of R1 as 19 degree in equation number 2, we will get the value of I. So solving for the value of I, we will get the value of I as 30 degree. Thus, for the angle of incidence of 30 degree, we will get the total internal reflection on the second face of the prism. The question says that a card sheet divided into a square, each of size 1 millimeter square, is being viewed at a distance of 9 centimeter through a magnifying glass. A converging lens of focal length 10 centimeter held close to the eye. Now, what is the magnification produced by the lens, and how much is the area of each square of the virtual image? So the question is saying that there is a convex lens of focal length 10 centimeter, and in the front of convex lens there lies a sheet. Let us assume it over here, and it is 9 centimeter in front of that convex lens, and on the sheet there are divisions pattern of a square, each of area 1 millimeter square. So we have to find out what is the magnification produced by this lens and what is the virtual area or the area of the image produced by the lens. Now, how to approach this question? So the first thing over here is we have been given the value of object distance, that is minus 9 centimeter with the sign convention, and we have been given the focal length. So for the position of image, we can calculate the value of V. Now we also need to calculate the area of this virtual area of this square that would appear from the eye. So we need the value of magnification by the lens, and it is given by V divided by U, that is the position of image divided by the position of object. So here only V is the unknown quantity, and we can use the lens formula in order to calculate V. So we can get the value of magnification. Now the second question is saying that what is the angular magnification, magnifying power of the lens? So we know that the angular magnification and the magnification is different. We have to calculate angular magnification as well. And also the third question is the magnification in case A equal to the magnifying power or the angular magnification? Explain. So let us proceed with the unknown quantity V, that is the position of image. Now substituting the values, we have been given the value of U as 9 centimeter, and with sign convention it would be minus 9 centimeter. Focal length as 10 centimeter. We will get the value of V as minus 90 centimeter. That is, the image is produced on the left side of this convex lens on the side of the object at 90 centimeter. Now we can calculate the value of magnification for the lens, that is V by U, and we will get 10. Now we know that the magnification produced is 10. So let us assume the virtual area of the square be A dash, and the given original area is 1 millimeter square. Now we saw that the magnification produced is 10 times, so 1 millimeter will appear as 10 millimeter. Now 1 millimeter square will appear as 10 millimeter cross 10 millimeter, that is 100 millimeter square. Since the linear magnification is 1 millimeter and area is having 2 dimensions, so we can say that 1 millimeter becomes 10 millimeter, and the area subtended by this 10 millimeter would be equal to 100 millimeter square. So the two questions are clear. Now let us move towards the angular magnification or the magnifying power. So we know that angular magnification is defined as the factor by which image on the retina gets enlarged. Now it is given by visual angle by the final image divided by visual angle by the object. and visual angle by the final image will depend upon the image position. So for this case, the image position is different than the value of d. So the angular magnification formula would be equal to d by f. So we can get the value of 2.8. Now there are cases when this magnification is going to be equal to the magnification produced by the lens, and in that case the image is formed at the least distance of distinct vision, that is equals to d. So in this case, what is happening is that image is forming at minus 90 centimeter. That is why this value is different from the magnification of the lens. Angular magnification is different from the magnification of the lens. If this value, if the position of V or the final image is minus of D, then we can say that angular magnification is equals to magnification of the lens. The question says that at what distance would the lens be held from the card sheet in exercise 9.22 in order to view the squares distinctly with the maximum possible magnifying power. Now here it is asking what is the distance of the object from the previous question so that we can view the image properly with the maximum magnifying power. Now this question is taking the data from the previous question, and the data are focal length of the convex lens was 10 centimeter, and now here we have to find out the magnification, the magnifying power or the angular magnification for the image to be formed such that the eyes could see distinctly. So for the squares to be visible distinctly, the image should form at the least distance of distinct vision, that is 25 centimeter away from the eye. Now so that we can deduce from this is that v should be equal to minus of 25 centimeter. That is, the final image should be at least 25 centimeter away from the eyes. Now so we have got the value of v, we have the value of f. Now we have to find out the value of u such that this case is met. Now here we have to find out what is the magnification in this case as well. Now here this magnification, the value of m is going to be equal to v by u, and whereas this is small m, the magnification is represented by small m, and the magnifying power is represented by capital M. So we have to find out the magnification as well. So we have to find out the value of u so that we can use the formula v by u. Now we also need to comment that is the magnification equal to the magnifying power. Now we have to comment that is this magnification equals to the magnifying power. So we have the formula ready that is to be used, that is the lens equation. So 1 by v equals to 1 by v minus 1 by u equals to 1 by f. Now here 1 by v, we can put the value of v as 25 centimeter. With sign convention, it would be equal to minus of 25 centimeter. We have to find out the value of u, and the value of f is given, that is 10 centimeter. Now the value of u from this calculation is minus of 7.14 centimeter. Now here we know that angular magnification is given by d divided by u naught, or the distance of object from the object. So this is the angular magnification. It comes out to be a value of 3.5, and this is the magnification. So this can be given by v divided by u, and this is same as the angular magnification. Now here we have found the value of linear magnification in this case, and we saw that is the magnification equal to the magnifying power in this case. Then we saw that the answer of this question is yes. Now how did this happen? How did the magnification become equal to the angular magnification? So we know that now angular magnification is given as the visual angle formed by the final image divided by the visual angle formed by the object at D. Now the formula for angular magnification is capital D upon u naught, where u naught is the object distance from the objective or the lens. Now linear magnification was given. Now magnification is given as v by u. Now here we saw that in this case, when the final image is at D, then we can write v as 25 and u is the object distance. So we can write it u naught. So we can see here that m is equals to m. Capital M is equals to small m, or the angular magnification is equals to the linear magnification. So we can say that whenever the final image is forming at D, then we can get the angular magnification is equals to the linear magnification. The question is saying that what should be the distance between the object in exercise 9.23 and the magnifying glass if the virtual image of each square in the figure is to have an area of 6.25 millimeter square. Would you be able to see the squares distinctly with your eyes very close to the magnifier. So we have been given the desired the area of a square that is desired, and we have to find out the object position for the desired area. Surface area. So we can say that A dash is 6.25 millimeter square, where A dash represents the area of the image. So we can deduce from this the length of each square. So length would be the square root of this area, which will give us 2.5 millimeter. Now we saw that in this question number 9.23, the length of each square and the width of each square was 1 millimeter. So upon magnification, it is going to be equal to 2.5 millimeter. So we see here that linear magnification is going to be V by U, which is the final length divided by initial length, that is 2.5. So we can say from here that V by U would be equal to 2.5. Now here we are desired to find this value of U. So now we have got the value of V in terms of U. We can write V equals to 2.5 U from this relation, and we know the focal length of this lens, which is 10 centimeter. So there is only one variable, that is U, to be used in the lens equation. So we can find out the value of U. Now later we have to say that we have to comment on, would you be able to see the squares distinctly with your eyes very close to the magnifier? So for this value of U, we be able to see the squares distinctly with your eyes? Now, in order to see the squares distinctly, the minimum distance should be equal to D. So let us find out whether U is greater than D or whether U is less than D. If U is less than D, then we won't be able to see it, and if U is greater than D, then we will be able to see the squares distinctly with our eyes. So let's use the mirror equation. Let's use the lens equation to find out the value of U first. So 1 by V minus 1 by U would be equal to 1 by F. Now 1 by V in terms of U is equals to 2.5 U. Now 1 by U is as it is. Now 1 by F would be equal to 1 by 10. Now the value of U calculated is minus of 6 centimeter. That is, the object should be 6 centimeter away from the objective or the magnifier. Now here we can see that the least distance of distinct vision is 25 centimeter, and U for this desired area is minus 6 centimeter. So U is less than D. So we can't see the square distinctly.